It's a great pleasure to have Suneeta Vardarajan and channel about online and algebras.
So thanks a lot for the invitation to visit this place. I'm giving two talks, so these are slides for both the talks. So I'll go, you just let me know when to end today's talk, say 1 hour or something, and I will continue from that. Okay, so I'm going to talk about some recent work which I have done with my student Mohammed Ali on the connections between polynomial algebras and mathematics. So what we will do in this talk, we will mainly discuss ways to prove the generalized second law in semiclassical gravity using techniques from polynomial algebras. And towards the end of tomorrow's talk, I will also discuss a new proposal by Destro and Liu to describe stringy horizons in the language of algebras and its connection to higher curvature. So this is some recent work. Okay, so let's just start by remembering what is the generalized second law. So the generalized entropy was introduced by Bekenstein in order that the second law of thermodynamics be valid near black holes. So if you throw something into a black hole, thermodynamic entropy of the outside has decreased. So in order to preserve the second law, you have to actually postulate that black holes have entropy, and for any spatial slice intersecting the horizon, the generalized entropy is the area by 4G plus S out, which Bekenstein originally thought of as the thermodynamic entropy of the outside. So he also proposed the generalized second law, which is the statement that this generalized entropy never decreases in time in any process.
So this is what these, in recent discussions, people call coarse-grained entropy rather than fine-grained.
This is the coarse-grained entropy, just in semiclassical. So what if we take quantum fields outside the horizon, and then what should we take S out to be? So Sorkin pointed out that it should be the entanglement entropy, where rho is the reduced density matrix of the black hole extent. However, this quantity we know has a UV divergence. There is now a lot of evidence for the idea that the divergence in the renormalization of G in the first term cancels the divergence in the entanglement entropy, and the sum total of these two terms is fine. Now, there exists a proof of the generalized second law already. This was true. Yeah.
This is entanglement entropy between inside and outside of the black hole.
Of the black hole.
So suppose your spacetime has some gas which has a lot of entropy, but it's not entangled with the black hole. That's not counted in this session.
That's counted in the outside.
So that where is it? This Sn you said was entanglement entropy?
Yes, Sn is the entanglement entropy of the outside. Quantum fields is outside with the. So we are just assuming there is just a black hole and there are quantum fields.
Right. So suppose I've got some excitation that the quantum field is far away, not entangled with the black hole. That does not.
That will not contribute to this.
Well, I mean, general Sn is the one-line entropy of the reduced density.
Yes. So you compute the reduced density matrix by just tracing out the inside.
So if there's a gas of unentangled particles, it's in a mixed state, then it will.
Yes.
Wait, sorry, please say again what Sn is. Sn is entanglement entropy of what?
Of the quantum fields in the outside with the entity.
I see.
So just find the reduced, just take the full row and then find the reduced density matrix and do minus trace row log. That's it.
But I was trying to that is something like fine-grained entropy. Right? I mean, I was trying to suppose you had a gas in a pure state outside. Thermodynamically, we often associate an entropy with it, but you would not do that, right? If it was in a pure state and unentangled with black hole.
Yeah.
But if it's in a mixed state.
If it's in a mixed state. But then this is really distinguishing between very things that are hard to distinguish. So isn't this what one understands would call fine-grained entanglement?
No, this is coarse-grained entanglement. Okay. There's always increases.
I see. What is the fine-grained entropy?
The fine-grained entropy is something you would do when you take the full partition function, right?
No. I mean, what I meant was that they have this island formula.
Yeah, they have an island formula. The island formula is a formula in semiclassical gravity, but the way it is obtained is by looking at these replica wormholes.
Correct.
So the way it is, it is a fine-grained. It is some semiclassical expression. That's it.
I see, but sorry.
And it's not the generalized entropy of the black hole horizon. It's the generalized entropy of the quantum extremal surface.
In their review, for instance, they distinguish between these two notions.
Yeah, they distinguish between these two notions. That's correct.
My understanding was that a gas in a pure state, in coarse-grained entropy, would be counted as having entropy. But that is not the case in your definition.
No, in my case, I'm just telling you exactly what this ascent is. It is the reduced density matrix.
Thank you.
If the full state is a pure state, then it's entropy is zero.
Yeah, if the full state is a pure state, full state of the interior and the exterior, right? Now you're tracing over the interior. So you have a reduced density matrix. You take minus trace rho log rho.
So the trace rho log will be zero only if rho is a pure state.
Yeah,
Even
which is
after
not,
tracing
because
of
I've
the
traced,
infinite
that which cannot happen.
Unless there is unless they are completely fractal.
Yeah, exactly.
To clarify Shiraz's question, the point I suppose is that if you just compute this quantity for a general surface, then that is sort of like a post-grain. But if you do the quantum extremality prescription, then that would be computing a fine grain.
Yeah.
So say that what do you mean general surface?
Like you just
Any
define the
surface,
surface in
not
some age and
not
then-
extremized.
Yes,
over
yes.
there.
I think the interpretation would be of that post-grain,
I see.
but which would be the case here, right? Because you're not particularly looking at extremal surface.
I'm not looking, trying to identify an extreme.
Okay. Yeah, maybe I misunderstood. But a fluid, for instance, which was in a pure state, would in this thing be assigned entropy? Okay.
I mean, bulk entropy.
Yeah, any entropy would be.
Yes.
Let's say, if it was not entangled with the back,
That's right.
it's in a pure state.
Yes.
Whereas oftentimes in thermodynamics we associate an entropy.
Yes.
Right. So this in my mind was the distinction that you're being doing something exact or.
Yeah.
Suppose there is some non-gravitational system.
Mm-hmm.
There would not be this 1 over g Newton to cancel the divergence coming from the entanglement entropy. So there's something special about this gravitational system.
That's what we're going to see actually, that the whole story which I'm going to talk about today is something special when you include gravity.
But with this interpretation of S int, is there still a increase in second law?
That's what we're going to show.
Fluid?
That's what we're going to show.
Just to
If Sn is minus trace rho log rho, where rho is the reduced density matrix of the exterior, then we are going to show that there is a generalized. Actually, the generalized second law has already been proven in 2011. Okay, the only thing is that in the proof there was an assumption. There was an assumption that certain quantities which Wald manipulated in the proof, like entanglement entropy and the boost energy, are actually finite. There was an approximation. I mean, there was an assumption that there's a renormalization scheme that renders these quantities finite, and then the proof of the GSL follows. But that assumption was never shown to be true until Witten and later these people, collaborators of Witten, what they did was they did something which.
The previous version of centralized second law is also true, and this version is also true. Both versions are.
So the if you just have S out being thermodynamic entropy of matter outside, right? Then in a lot of examples, people have already shown that it is true. They've taken thought experiments involving several systems with thermodynamic entropy, and they've shown it's true. Now, when you take quantum fields and you take this to be the entanglement entropy, then Wald's proof applies. Okay, but Wald's proof assumes that there is a renormalization scheme that renders this entanglement entropy and the boost energy finite. So he takes things which are actually formally infinite, he manipulates them and gets the GSL. So there is an assumption. Okay, so that's the assumption. So that's the renormalization scheme which these people proposed. Okay? They proposed a renormalization scheme using techniques from Feynman. So I'm going to get into the details. So what they did was they described a statistical entropy of an algebra, and the algebra in question is the Feynman algebra of observables in the Blackboard XD. So I'm going to get into the details of that. So let me just tell you what they showed. They showed that the generalized entropy of, say, the Schwarzschild black hole at its bifurcation surface is exactly the statistical quantity, which is the entropy of the algebra, modulo a constant. And they also proved the version of the generalized second law after implementing this renormalization scheme. But there is an assumption there. There is an assumption that there are some early times and late times, and in between the early and the late times, no matter falls across the horizon. Okay. So if the black hole is just allowed to equilibrate between the early and the late times, then they prove that the generalized entropy increases, comparing the late time and the early time. So this is not quite a local generalized second law, which would be the statement that P S gen by dV, where V is the affine parameter along the horizon, is greater than or equal to 0. So this is not quite a local.
So the idealized version of these assumptions doesn't account for black hole.
I'm sorry.
The idealized version of these assumptions doesn't account for black hole.
Yeah, you can also do it for one-sided black holes now, but they took eternal now.
Sorry, for the generalized second law, you would need to define algebras all along the horizon. Right? Not just
There is an algebra all along the black hole exterior, not just on the horizon. You need the algebra on the horizon also, that's true.
So in their proof, if the entropy decreased a little bit from early times and then increased more, that would.
No, they don't. They assume that no matter. So let me just show you this diagram. Yeah. So here is the early times. Some matter is falling.
So I see. So in your proof, what you want to do would relax that assumption.
Yeah, matter. And so it would be a
in that
local.
case, what actually happens is that early time to late time. So when does the entropy? If there's no matter falling in.
Yeah, so there is some matter which falls in at early times.
Yes.
Then there is a long time during which the black hole is allowed to equilibrate.
Okay.
And then there is some matter that falls at late.
But while it's equilibrating in their proof, we don't know that the entropy is increasing monotonically.
Yeah, we don't know. We don't know that d S gen by dV is greater.
Yeah, so it could dip and increase again.
No, it won't dip and increase because there is no matter falling
No, it
across.
shouldn't, but I'm saying their proof doesn't.
Yeah, their proof.
If you are sure that this doesn't happen, then the proof is valid for all.
Yeah, we are not sure that it doesn't
not
happen.
sure.
You can have matter falling across at any time. That's why it doesn't apply to that.
I get that two different things here. One is where matter is not falling in.
Mhm.
But do we know what? So the black hole
When
is
matter, if
equilibrating,
you have a
but
stationary horizon and
Yeah.
nothing falls in
Then-
and it's not radiating,
Yeah.
then nothing will happen.
nothing happens.
Yeah, so its area will remain constant.
Simply.
Now, what they're assuming is something falls in at some time, and then after a long time, something else falls in. In between, the black hole is allowed to equilibrate.
Okay.
And then they showed that the generalized entropy at
So it's
late
really
time.
a special system there.
Yeah, it's a step. So what they got was a renormalization scheme which renders the quantities which Wald was manipulating finite, but they didn't have a local case.
So if I have a system that just the black hole is evaporating,
Hmm.
then the way this work out is that
This proof would not apply. Because it will be evaporating at all times, right? It will not be evaporating at some early time and then there is a long time over which nothing happens and then at late
so
time.
just to see that it is true, that would be like it would remain this S gen would remain constant.
No, S gen would typically if you have
No,
working radiation,
yeah.
S gen would be greater than or equal to 0. S gen by dV would be greater than or equal. Even
But,
so, if you consider the entanglement entropy of the quantum fields and of the black hole, then this combination never decreases.
Yeah. No, but just if I have a evaporating black hole. at the
Because
thing ends-
evaporation is also.
No, I was just wondering that the entangled radiation would come out and correspondingly the black hole area would also decrease.
Yes, but the combination never decreases is the statement of the GS.
Combination should remain constant, right?
No, the combination will not remain constant. The combination is never decreasing.
No, I mean in general cases, yes, but I'm saying this particular case where nothing else is happening, just black hole is evaporating.
Yeah, but this proof of Britain does not apply to that situation, right? What they're saying is there is nothing.
Just trying to understand how this would work. The generalized second law.
Yeah. So we have to prove the generalized. We're not, and what I'm saying is there is no such proof for the Hawking radiating black hole as yet.
No,
But he's not talking about proof.
I'm trying to understand intuitively what will be the statement there.
The statement
Just
will
from
be
this
that
picture.
T as 10 by dV is greater than or equal to 0. It will not
the
equal.
question is that if it's evaporating and nothing else is
I
happening.
thought the area would reduce in the same rate that the entire is.
I think you're talking about the fine grain.
No, the formula that you wrote, the area plus S end,
Yeah.
that would be 0, right? The derivative of that or not?
So what
Yeah.
you're saying is this keeps on decreasing.
Yeah, and that.
Yeah, but then this entanglement entropy should compensate for it.
Yes,
But together it would be 0, right?
That's not the statement of the GSS.
No, because the GSL doesn't assume that the black hole is only evaporating.
Many
Yeah.
things could happen and
Allows
allows
other things
this
to
particular
happen,
case.
which could increase the total entropy.
Just to understand that I'm
Just to
understanding
understand
you that
purely evaporating black hole in.
Initially, this increases, right, as then.
So I'm just trying to understand
Or
whether
an evaporating black hole when it starts evaporating.
Why do you say it increases? Area decreases, entanglement increases. Abhijit is asking, are they exactly those two?
I mean, page though we see that it increases.
We just compute the entanglement entropy outside, that increases. But he's looking at entanglement entropy
plus
plus.
area. Plus area. Okay, let me just get to your question later.
Okay.
I think it is, I'm just confused whether what you're talking about is the fine grain entropy and not the coarse grain.
What would that mean, the fine grained
The fine grain entropy is, in the sense of what all these people have done, the one which reproduces the page turn. So after the page turn, that entropy decreases, right? It decreases and becomes exactly 0, rather than increasing all the time. So I think of the GSL as describing a coarse grain entropy, not a fine grain entropy.
Okay.
But if it comes from extreme, if the fine grained entropy comes from, in the semiclassical limit.
No, the fine grain entropy is given by a formula which you can write in the semiclassical limit, but it is computed not in the semiclassical.
Yeah, I agree, but I'm saying that fine grained entropy, there's a minimum, you have to minimize over all extremal contributions.
Yeah.
And at early times,
So when you minimize over all the configurations, all the possibilities, you will get something which you can write using semiclassical gravity, but which decreases after the page.
Yeah, I'm saying that there are discrete choices and minimization. It's not a continuous choice. And if this formula at early times gives you the right answer for fine grained entropy, and we know that fine grained entropy won't increase.
Yeah, but this entropy could increase after the page. Right?
No,
It need not decrease because it's not the fine grained entropy. This is not the quantum extremal sense. This is just a cut of the block. Anyway, let me just get to this. Okay, so I just want to now describe, this whole polynomial algebra construction of these people and how it provides a renormalization scheme and how we can use that to prove the case.
So what's B in DS over D?
I'm sorry.
What's B in DS over D?
It is a fine parameter along the horizon. So this computation, whatever these people had done, actually generalizes to black holes in an arbitrary diffeomorphism invariant. So this we proved a couple of years ago. And when this generalizes, this generalized entropy contains the Wald entropy at the bifurcation surface instead of the area bifurcation. So what these people did in order to renormalize divergent quantity was to.
This works for, so what statement works for this, this with the end? It works for.
Ascent is always the same, but in what we showed was that in a diffeomorphism invariant theory, you replace area by 4G by Wald entropy.
Yeah.
And then it works.
No constraints
Wald-
on the kind of higher derivative corrections.
No constraints on the kind of higher. It should be diffeomorphism. And then you can use a covariant for space formalism.
China theory was also had similar kind of results, or but she
just
got some constraints. I remember she kept this problem as an open problem, right?
Yeah.
Not of this, yeah.
But for her, what was open was this non-linear evolution. Let's see. Yeah, I mean, for instance, first order and amplitude expansion, Wald, and then Shantani and friends. That's very clear.
So actually, I'm not going to talk about this particular result. I'm going to talk about the proof of the GSL for Einstein gravity, because this is not. So what we did was we showed that whatever Britton and collaborators could do, we could do the same thing for black holes in an arbitrary diffeomorphism invariant, which is basically this defining an algebra entropy and then doing the same thing which they did, that between early and late times, if you don't allow matter to fall in, then the GSL is true. So I'm now going to talk about a local GSL, which we have proved in Einstein gravity. And then I think it also works with some details for higher curvature gravity, but we've not worked out it.
So this extremal surface, does it keep on changing with time?
Yes. There is an extremal surface before the page time, and there's a completely, which is the empty surface. And after the page time, there's another extremal surface, which is why this, this course of fine-grained entropy follows the page.
So a priori does not expect that. I mean, this is somewhat of a vague question, but that for arbitrary diffeomorphism theory, this should be true.
No, actually, it's quite surprising because there are problems with higher curvature theories, right? There are various, they're not well posed, and there are a lot of problems with them. But this result does not seem to meet those. Does not have a problem with those. Okay, so what Chandrasekhar and Pennington and Witten did was they used an algebraic procedure in von Neumann algebras called the cross product, but still they did not get the local GSL. And what we will show is that you will get the local GSL in all cross product constructions with no assumption on matter falling across the horizon at different times. And this also works for asymptotically flat black holes like Schwarzschild and Kerr, whereas their proof was for asymptotically ABS.
What is the word local?
Local is d as gen by dv is greater than.
Not in terms of an entropy current.
No, but not in terms of saying that between early times and late times the generalized entropy.
At the linearized level, there is I think Shantani and friends have shown that there is an entropy current that we can associate. So
that is for generalized entropy or for
I believe it's not
classical.
I mean,
Classical.
Yeah.
Right.
Okay, so I just thought because I was asked to summarize von Neumann algebras, I just thought I will quickly summarize von Neumann algebras. I'm sorry if you all know this already. Then let me
we
know.
probably don't, Suneeta, and you'll also summarize what this has to do with the stuff you were talking about.
Yeah, we are going to do that. We're going to do the proof of the GSL.
Yeah, as much as the proof, just intuitively, what these algebras have to do with
what
things
is
you've been talking about.
Yeah, what is the physical connection between the cross product and this particular question? Yeah. So let me just quickly tell you, just let me run over the definitions. So we say an operator is bounded if you have operator acting on Hilbert space is bounded if you take all normalized psi in the Hilbert space and O psi norm is less than or equal to that bound, that quantity. The infimum over all such K is the operator norm. And if you take the set of all bounded operators on a Hilbert space, then they form an algebra. Because you can take linear combinations, multiply them by a real number, and so on, and everything would be in the space of bounded operators. So it forms an algebra.
Okay, that was very fast.
Yeah, it's fine.
Only bounded operators is going to be a pitch.
So K, the infimum over all K is operator norm, and now you can easily show that if you have.
On what infimum is, I think it means least upper bound probably.
So
the lowest K.
Yeah, so I'll take the lowest K.
Yeah, that's the least upper
bound.
It's like the lowest eigenvalue of this operator if it was a finite operator.
Yeah.
If it was a finite.
The lowest eigenvalue is the operator norm.
Yeah, because it's the action of O on psi and the smallest
number you get.
Yeah.
The largest eigen.
Oh.
So the largest thing.
The largest.
Infimum.
Because
large.
No, here wait. You take all the size,
And
then
then
you
take
do
the
norm
smallest
I, and you take the smallest one.
It's the lowest side.
All, no.
It's bounded by that.
It is already bounded. It is bounded by something.
In matrix language, it's large.
Largest side. It's largest.
Because it's bounded by even higher than that, right? If the highest height value is
all
100, then
sizes.
200 also is bounded by 200, but you want to minimize that to 100.
It's bounded for all sides. You have to take the worst side, which makes it large.
Yeah,
to
you-
check that.
You just take all the size and you write this
Oh, I see.
this inequality.
The one that's written is the bound.
I see. So it's the lowest bound. Yeah.
What do you mean by 80?
80 is some complex number times.
But that then A can be, I guess, anything. Yeah, it's anything. Yeah.
So now a star subalgebra of this algebra of bounded operators on the Hilbert space is one which contains the adjoints of all the operators. And then what we can do is we can take this algebra, the star subalgebra, and then you take all the limits of sequences of operators in the algebra and you include those limits in your algebra. That makes it a Von Neumann. So the commutant of an algebra.
So
Yeah.
generally, when you include limits in a space, that's what defines a compact space. So it is some kind of compactness for algebra.
It's
Intuitively.
closed.
Closed. Closed. Sorry,
Yeah.
Closed. Yeah, sorry, I meant a closed space.
Yeah, just closed. It's closed.
Then there's some issue of limits where you take limits on states or you take limits on expectation values.
So here I've defined precisely what is.
So this is
I'm
the
just
one
taking
where you take
expectation value.
matrix.
Be clear.
I'm sorry, if you could give us an example, like let's say for instance in one.
For example, let me just give you an example. Let's say you have two Rindler wedges of
Too complicated. One dimension quantification. X is not a bounded operator clearly, but is it a limit of bounded operators?
is X, okay. Here I have some other X and Y, so I'm getting confused. Your A is like X, right?
Yeah.
X is like X.
X in quantum mechanics is clearly not bounded because I can find a normalized state which has a as large as value as I want.
Yeah.
But is it a limit of bounded operators and why is it a limit of bounded?
I think you can, I mean, if you look at expectation value X operator on any wave packet, that will give you a finite answer.
On any wave packet, and I move my wave packet and I can make it as large.
You're fixing the states. X and Y are fixed. You're changing.
Yeah, you are having the sequence of operators. You are looking at the matrix elements of these operators. So you're basically looking at these matrix elements and letting.
Oh, so X is a bounded operator. Just like.
Yeah, I don't know. It's not clear even its limit or not. It's not clearly not bounded, but even if it's not clear to me, it's whether it's a limit of something.
You have to make a sequence of operators which converge to it.
But first question is it bounded by itself? That is clearly no. Because
No,
I can
it's
clearly
not,
find a
it's
state
not.
which makes it as large as possible.
Yeah, it's not.
Okay, now, you're explaining that it is a limit of operators?
Yeah, I was using wave packets.
Okay.
But from classified space, if you take that, let's say, apply periodic boundary condition, we'll take that.
No, you're not
Because now
supposed to
we're taking
change
a
the
limit of
theory.
Hilbert space.
Yeah, not supposed to
Right.
change the theory.
Yeah. Oh, right.
Using bounded operators, you use exponential.
Yeah, I was just thinking
E to the I.
We are going to do that.
You're-
Yeah, we're going to do that. Okay, so now let me just quickly say what is the commutant of an algebra. It's the set of all bounded operators which commute with every element of that algebra. And there's a theorem which shows that this is a Von Neumann algebra even if the original algebra was not. So actually the commutant will include all those limits. That's the point. Like even if my original algebra was not a Von Neumann algebra, but once I take its commutant, it will include all those limits. So it is always a Von Neumann.
What makes it one? What makes the algebra one Neumann?
Just you should include the sequences of limits of all.
So to try and include the X operator, would I do E to the I?
You can do that. You can do that. You can do that.
that's
You
very
can-
good.
I think that would.
Yes.
So
And why is e to the power epsilon x?
I epsilon.
I epsilon.
I epsilon.
I epsilon.
That is bounded because of the phase.
Yeah.
Nice.
If you try to.
Explain of the star algebra is.
And so
Is it already is already a star algebra?
yeah, S need not. Yeah, S I think has to be a star algebra. But after it need not be a Von Neumann algebra on its own. It need not include those limits. But the commutant will always.
Sin x. Sine.
No.
Sine X.
No.
Sine epsilon X squares.
By epsilon.
Yeah.
Okay, now alternatively, there is a theorem which tells you that if you have a star algebra which equals its double commutant, then that's a fundament. Okay, so what are the algebras that we are interested in? We are interested in QFT algebras in a region of some arbitrary curved spacetime. And if you now look at just the quantum field phi of x, this does not have finite norm because we know that phi x prime in any state, expectation value in any state, the limit that x goes to x prime is infinite. So phi of x itself is not a bounded object. So to form an algebra of quantum fields, what we have to first do is we have to smear the field. Okay? So we have to smear the field with some function of compact support in some region. And then we have to consider bounded operators made from this smeared field. Okay? For example, I just given e to the I phi f, which we just mentioned. And then we have to close the algebra under weak limits, and then we get a quantum.
You're dumping
Space and time.
in time.
Space. You have to take smear in time. Just smearing in space is not enough to give you an operator of.
Right. But I was asking whether it's in real time or you think.
It is in real time.
Yes.
Yeah.
Sorry,
Now-
even the smearing, how would that fix the problem?
So the
Maybe-
smearing
Assuming point function, then that singularity.
will get fixed by smearing in time. So there is the old paper, very famous paper, which talks about the smearing. The abstract of the paper itself is that you need to smear in time, and then you will get this operator of finite norm. And there's some paper of Witten also recently where he takes examples of several quantum field theories. And there he shows that if you smear in time, then you get an operator which is finite norm.
The intuition is that by smearing in time, you can cut off energy, right? Like you can cut off the support of this operator.
Yes, that's
And that automatically cuts off the support in mind.
yes.
Once you smear in time, there's no difference between a quantum field theory and a lattice.
Mhm.
Once you smear space time.
Okay, so let me just define the quantities which I'm going to be working with. AU is the algebra associated with an open set U. So you take these smeared quantum fields in this open set U. So the smearing functions are all having support in U. And then you call this algebra A of U. And if U prime is space-like separated from U, then we of course know that these two algebras commute. So AU prime is actually a subset of the commutant of A of U. Now, if U and U prime are maximally space-like separated from each other, which is what we mean by causal, the word causal complement, then there is a proposal that this A of U prime should exactly be the commutant of A of U. And this is true for some examples. So, for example, the algebra of Rindler wedges, where we have smeared quantum fields on one right Rindler wedge and the left Rindler wedge, and then this statement is true.
It's not true in general.
It's not true. There are examples for it. That is not.
And it doesn't have to do with the connectedness of say, the spatial manifold or something. Otherwise, intuitively,
You think it
let's
should
say-
be
yeah,
true?
it should be
You
true,
think
right?
it should be true. I don't. Those examples are actually very complicated, so I don't know exactly geometrically what they mean.
What should be true? Something?
Is that the
A U prime should be a
yeah,
prime.
if you take the
Maximally space-like separated regions.
correct, you take U prime, which is separate spatially, then
And what
that
about
would be-
gauge theories?
So that's why I was thinking, if you had some non-trivial topology and you had Wilson lines or something, maybe there's some more structure, although even there.
Mhm.
But otherwise, let's just take R3 as a spatial slice.
It
That's what
should be true.
I would have thought,
Right,
right?
it is true, right? What was the condition for it to be true?
No, this is just a proposal.
It's a proposal, but it's not really,
Actuality.
yeah, it's not really always true. So I just wanted to understand when.
Yeah, so I don't remember those examples that
Okay.
become pathological.
I see,
but
okay. So usually it's true,
For everything I know, it is.
Sorry, but what about just the gauge theory, even in R3?
yeah.
The fact that it's not completely local.
So there you might talk about it, but with some twists,
You can define things.
Yeah, more or less it works out because it's a bit of a story because there's a center to the algebra, and so on and so forth, but
Yeah, just I was thinking total charge equals 0 could be plus here and minus here. That's that kind of thing.
that's true. That's true. Usually what happens is that therefore
You do the sectors and sector by sector.
Sector by sector it works, and that's like diagonalizing the sector, and it works out. It's not like in the end a radical.
Okay. What about in something like gravity, where the gravitational Gauss law, semiclassical? Would this work then? Sounds very anti-superstructure.
You should say, I don't know how. So is it sensible to separate things into space-like regions with each other given the light cone? This always worries me. Like, what does it mean for the light cone to fluctuate a little? Like, you are allowing some, Shiraz, in your question, you are allowing some fluctuations, right?
I was thinking even in perturbation theory, the fact that you know so much from infinity, does that spoil things?
I see that kind of person.
Yeah.
You know everything, right? That's what you would say.
But not in a complicated state. Yeah, yeah. But okay, later.
Yeah.
When you say U prime or open set, these are all space time, right? It's not spatial space.
No, not spatial space. Everything is space time.
U prime or open, is it?
U and U prime are causal complements of each other.
Yeah.
So they are maximally separate. U is an open set,
Is
and U prime
an
is
open
whatever
set?
is maximally separated from V.
So is it an open set? U prime.
Set.
I thought somehow in the first line U prime.
At least on the real line, the complement of open set would be close.
Yeah.
But maybe she means a maximally separated call.
It's a causal complement which is maximally separated, but in the example, let's say I take U inside a Ringler wedge, right? Then I think U prime would be closed because it would include the points at the boundaries. It will include the points along the
Does it make a difference from the algebra standpoint?
No, it's not really required for the algebra that you should know whether U prime is closed or not. I think that A U prime will include those boundary regions because it has to include the limits of all the sequences of operators. So I think it will include points along the boundary region. Okay, so now let's also talk about the center of the algebra. The center of the algebra is whatever is the common intersection of
So
A and A prime.
is AU by itself a one-Neumann algebra?
AU need not be a one-Neumann algebra. So in quantum fields, typically it is. Okay, but
So then why doesn't the boundary of this U also get?
so yeah. So if I take U and V prime, so if I just take some U like this, right? This might not include the sequences of all the operators.
I see.
So I have to take two regions which are causal complements of each other, like this. For example, this region. This is a function.
Just once. So I understand if we take that Ringler wedge, the causal complement is the left.
Is the left Ringler wedge, correct. This is the causal complement.
And the upper guy is not in the causal complement because it can get signals.
Yeah, it will not come in.
But we can discuss this in a space-like slice also, right? All these operators.
You can discuss them in a space-like slice, but this whole theory is for the full space.
So you need to smear over time as well.
You need to smear over time. That's the reason.
Okay.
Just smearing over space doesn't make it of finite.
And if you take the blob you drew earlier, which is not a one-Neumann algebra, is it not a one-Neumann algebra because of the limits or because of some algebra?
So it is not a four-Neumann algebra because it might not include the limits of all the operators.
But I can't just get into the Hamiltonian and evolve it outside the.
I'm sorry.
Is it even an algebra? Like, can I take the
It
Hamiltonian?
is an algebra, and okay, fine. So what you can do is you can use the Hamiltonian to evolve the operator out of that region which I showed you. So the algebra of this wedge is the same as the algebra of this region.
I see.
If you allow the quantum evolution.
Okay, but it just doesn't have the limits.
Yeah. So if you have to include all. First, you take a region, okay, and then you take all the field operators in that region, smeared ones. Then include all the limits, make it a four-Neumann algebra, and then you evolve them. Okay, evolve them using the Hamiltonian. Then the algebra of this wedge is the same as this one.
But previously, you would not call it a algebra, right? Because by itself, you could define something like just operators smeared on that small region.
No, the small region
That's
is the
not an
squaring in
algebra.
time also. This,
Yeah.
this is a region in space-time.
Yeah, but
It's not a- it's
that's
not
not
a-
an algebra, right?
That will be an algebra if you include all the limits of the sequencer form.
So, but
What I'm saying is you just take some quarter fields living here, smear them with functions of compact support in this region, then that's an algebra associated with this region. Now you complete algebra by taking all the limits,
Yeah.
then you get a four Neumann algebra. But the point is you can use the Hamiltonian to evolve. Suppose you have a Cauchy slice for this whole region. Let's say this is some Cauchy slice, and there is some region which is the domain of dependence of that Cauchy slice. Then the algebra of that region is the same as the algebra of that domain of dependence.
No, but you wouldn't call the set that you make out of that small region an algebra, right? Would you? Is it an algebra?
No, you can have an algebra with any open region in space-time. By including those limits, you have to include the limits.
And it became a four Neumann algebra, right? Because we included the
You include the limits, and then that four Neumann algebra is the same as the algebra of the domain of dependence.
I think Abhijit was asking, since you can evolve it,
Hmm.
that's like taking products of the Hamiltonian with this
Yeah.
set, but maybe infinite number of products. Is that the reason that it's not?
No. E to the I h is the better operator for them anyway.
Okay, good. So,
TIHT is a good operator.
so then, along the lines of Abhijit's question, since you can take this operator by evolution to the other guy, by itself it would not be an algebra, right?
Why would it not be an algebra?
Because you multiply by something that lies in your algebra, e to the pi ht,
Mm-hmm.
and multiply by e to the pi
No, at first,
minus h.
yeah, so first you,
H is not part of your answer.
H is not part
Why
of
not? You could make H out of these the fields in this region. This funny region.
H is in general
No,
complicated.
H is
over
no, that's the part of H on your H.
Yeah, what you're saying is for a Cauchy slice, you can evolve a Cauchy slice for that region. Right?
Let's take a little band around a space. Take your inler thing and take a little band in time around a space, a spatial slice.
Okay, yeah.
Just some little band around.
Yeah. Little
Now I
band
can
around
make
which
H
is
out
enough
of
to
that.
smear
Oh,
the
I see.
fields.
Okay, and now we can evolve. Yeah.
So now you can evolve.
Just to be, strictly speaking, you will have the edges coupling to the next nearest neighbors right outside. So you have to be a little careful in a local theory to isolate some part and say there's a Hamiltonian that just.
No, the problem is, if I just take this, for example, this point here, this is a sphere, right?
Sphere.
Yeah, so if I try to smear the field operator on the sphere, that's not enough to make it a finite. So basically, you should smear fields over an open region.
Yes, open region. I thought Shiraz was trying to define a local notion of a Hamiltonian by integrating a Hamiltonian density.
Yeah.
And since you're trying to do everything very precisely
There'll be some ambiguity around the edge.
around the edge, but it's important because, suppose I put it on the lattice, that's the only way I know how to make a local notion very precise. Then the edge will couple to the nearest neighbor and that will couple to the nearest.
But by causality, it will stay on the ambiguity will stay on the edge. Then it can't, by causality, leak into the solution.
We'll just place the domain of dependence.
The natural Hamiltonian which leads within the spindler is the boost upgrade.
So,
I'm sorry.
There's a natural Hamiltonian which leads within.
Within the wedge, yeah.
so the boost operator,
Exactly.
boost operator is fine if that's what you mean. That's what explains the Minkowski.
No, boost up.
Boost up.
But I think that she's allowing because she's allowing the causal development within the diamond, right?
Oh, but just to say,
Outside the diamond.
No.
Side.
I'm sorry.
Abhijit was saying this or this thing here would not be closed under evolution, right?
Under boost.
Under boost.
This thing will not be closed under boost. That's correct.
Correct.
That's correct.
And
That's
therefore,
correct.
but since boost you can build out of operators here, is not by itself an algebra. That was his point, if I understood right.
Yeah.
That's only consistent to take the whole thing. That was his point.
I thought the answer was that she's defining the algebra of this thing to be the closure of all of the things.
Yeah, if you can just close
There's
it.
no question.
Yeah, you can just close it, right? You can just close the algebra.
Which is just the set of operators obtained by smearing in some.
Yeah, but I
Yeah, but then you can close the algebra. You can close the algebra under which limits
You
and
cannot say close the algebra because it's
Close the
not
set.
algebra to begin with.
close the set.
Yeah.
Close the
Plus,
To
Yeah.
begin with, this was not an algebra,
Yeah,
right?
yeah.
Okay.
So I thought that was a definition. So the next question is then under what circumstances? So I asked the first question because you said that it is not a phenomenon. So what circumstances it's not a phenomenon?
If you don't include those closures of those, if you don't include the sequences of all.
So you can close it as an algebra.
So what you can do is, I'll tell you, you start with an algebra, okay, and then you take its double commutator. You make it into a polynomial by taking its double commutator.
So the statement
This
is
is just an
all algebras is related to the beginning of phenomenon.
Yes, you can, because you can take the double commutator and rotate.
Yeah, I'm really sorry, please excuse me, I came late, but if you already defined what a phenomenon is, sorry.
Yeah, it is an algebra.
Just once, can you just define it?
Yeah, so it's an algebra which equals its double commutator, or equivalently, it's an algebra which includes the sequences of all operators, the limit of the sequence of all operators. So for example, limit n tends to infinity from x, a, and y is equal to sum x, a, y. Then I include a. I also include.
This is equivalent to including to.
Taking the double commutator. So if you want to make something into a fundamental algebra, you just simply take the algebra and take its double commutator.
And take the union. So
Yeah, yeah. Just take the double commutator of that.
Okay, I see. But that has to be nice.
Can I ask a question about
Yes.
the center? You just
Yes.
defined this factor, rather,
Hmm.
concept of
Oh,
factor.
yeah, sorry, I forgot to say that.
You said that you said that, I think.
Yeah, every
But-
fundamental algebra is a direct sum
So
of
just let's take one fundamental algebra which
Mhm.
has a center, non-trivial center.
Mhm.
Now,
So the center is actually, it's a technical result, but let me just tell you what they do.
Hmm.
The center is generated by a particular Hermitian operator.
okay,
And that Hermitian operator, you look at the eigenstates of that Hermitian operator,
Hmm.
there will be a direct sum kind of decomposition
ah,
of those eigenstates
okay,
into various fundamental algebras, each of which is a factor.
okay, each of which has no
It-
center.
Yeah. So it's
And you have
it's
to
enough to
do
just
this
study
for
factors.
every operator in the center. You have many operators in the center. You
Yes,
have to
yes.
take all the possible combined.
Yes, yes.
I will just diagonalize them and then.
Yeah,
sum the
exactly,
theory
exactly.
of-
And there's some direct sum
Right,
decomposition into factors.
Sorry.
So there is a direct sum decomposition into factors. So if you have a non-trivial center, okay, now there are some operators which generate this non-trivial center. You have to look at in their eigenspace basis, and in that basis, you will find that the algebra decomposes.
So the center is no longer multiple of the identity, it's only multiple of identity inside.
No, if you have a non-trivial center, trivial center is multiple of identity.
I see, okay.
So you can break it up into factors.
The center can have continuous eigenvalues.
The center can have continuous eigenvalues also, I think that's.
So direct sum is some sort of a direct
It
integral.
could be directly. And it's. Okay, so now what we are going to do is we are going to take the classical black hole spacetime and we are going to consider the quantum field theory, quantum field operators in the left and the right part. Okay. So these two algebras are indeed, these two regions are causal complements of each other, and these algebras are really commutants of each other. Algebra of the quantum field operators in the right region and the left region. Okay, so now we come to something called the class, which is the classification of these fundamental algebras, which is just based on their properties. So the algebra of quantum fields in this subregion is actually a type 3(1) fundamental algebra in this classification, and it is a factor. It has trivial center, and the classification of these algebras is based on their properties. So let's just. Yeah.
Proper region, just once can you go?
Proper subregion is when it is not the full spacetime.
That's all?
Yeah, proper subregion is proper subset, which is a
And it
subregion.
includes limits, it's an open set or something, or just so since you're trying?
No, I think it includes the limits.
So,
Is it a factor even for Bayes theory?
Is it a factor even for?
Bayes theory.
For Bayes theories, I don't know. I don't know if it's a factor for this. So I'm only thinking at the simplest kind of scale of fields. Okay, so type 1 algebras are the usual algebras associated with, say, quantum mechanics, quantum mechanical systems. They have a well-defined Hilbert space trace. They have density matrices, that is, with the same Hilbert space trace, you can find positive operators such as trace rho is 1. And they have pure states. So an example of this is the algebra of all bounded operators on a Hilbert space. So it could even be the quantum field Hilbert space, but if you include all bounded operators, then that's a type 1 algebra. And type 1n has an n-dimensional Hilbert space, and type 1 infinity is just some algebra which has operators with infinite trace, like ID.
So if you took all bounded operators in a
Even in the quantum field Hilbert space, that would be type 1.
and it would be one infinity presumably or what? I mean,
It would be 1.
infinity.
It would be 1. Okay, now type 2 is the situation where you have no density operators in the area with the usual Hilbert space trace, but there's another renormalized trace, which is a linear function on the algebra, such that trace AB is equal to trace BA, and this condition is also trace A dagger A is greater than 0 for A non.
Sorry, Suneeta, just suppose I have a normal massive quantum field here, massive free scalar field, and I look at states built out in the Fock space. There is a pretty natural trace. So why? Oh, but because there's a region.
Yeah.
Yes. Okay.
Yeah.
The whole theory has a trace.
Yeah, the whole theory has it. The whole theory is type 1.
I see.
Now, type 2 is one where you don't have the Hilbert space trace.
But
Full algebra then does have a trace, right?
Yeah, full algebra has it.
So what was this example for?
just take a free massive scalar theory and build the trace out of the Fock space. Okay. In just the whole theory. Okay. The whole theory there, it has a good trace.
Yeah, it has a good trace, there are pure states,
Okay.
everything.
It's because you're carving out a region.
Yeah,
it has
yeah.
no trace.
What goes wrong in the region?
What goes wrong in a region, I
So
suppose?
in the region, you have to have a row belonging to that region, because of belonging to the algebra of that region, such that trace row is 1, and you don't have such a row.
In type 2.
In type 3, in type 2 also you don't have such a row, type 3 also you will not have such a
I think intuitively it's the fact that you cannot take finite energy states and localize it really properly to range. It's like that.
Yeah. There should be a calling.
Yeah.
And in the entanglement row will be infinity because of this.
Yeah, it's infinity because.
Trying to understand type 1 as well. Suppose I just took a quantum field theory and I said I'm going to project onto all states less than some energy level. I take every operator I project it like that. Would I get bounded operators or those are, what is a bounded operator?
So bounded operator is you take an operator, you smear it in a region of space-time, and then you take bounded functions of that smeared
Bounded function.
like for example e to the I5 n.
And just to we don't I can ask you later, but for example, if I just took a quantum field theory and said I'm not interested in very high energy states, anyway they're not accessible in any experiment. I just put a cutoff, project everything. Does that start becoming a type 1 system in some way? Just to understand.
Wait, are you taking the whole quantum field theory?
I was thinking.
Then isn't it? Yeah. Right.
The whole quantum field.
Then it's a type 1 theory anyway.
It is a type 1 theory anyway, but you can, I think, restrict and also keep it as type.
The whole quantum field theory is not type 1. I mean,
In the whole region, in whole space time.
Let's take it on a compact space, massive scalar field and compact space. First, that would definitely.
But he's saying if you take on lattice.
If you put it on the lattice, it's always type.
Let's not put it on that. Let's take the full quantum field.
But then the energy can go to infinity and so on. This is okay. I mean, I'm asking. I mean, of course, I'm saying oscillator energy can go to infinity.
I think so.
But no, this is okay.
It's the algebra of all bounded operators.
So
That's the type 1.
that's the type 1. But I just should have enlarged the question a little bit. So just to ask.
I'm saying there's a clear trace in that theory. We compute partition function of that
It's
theory.
not a Polynomial algebra at all. If I have all bounded operators, I'm not guaranteed that the sequence of bounded operators may not become unbounded. Isn't
It might become unbounded, but that's part of your definition.
Yeah.
That's why if you just include,
No.
I think perhaps Shiraz is saying, okay, bounded operators are an example, but we can even generalize the
Yeah,
case.
I think it's basically quantum mechanics.
For example,
Quantum
suppose if you
mechanics,
No, it's like put quantum field theory, massive quantum field theory on a sphere, it's no different from quantum.
Yeah.
So
So I mean,
So
but
the 2D behavior.
there's no problem.
It's only the IR behavior.
If at all. Yeah. I think the real problem is when you cut off some region.
No, but I can ask Sandeep's question for a region.
I mean, then let me ask you the following, so just to internalize this, so, okay, any quantum field theory.
if you put a QFT on a lattice,
No,
that is
lattice,
a type
of course,
one.
we will
That is
have
type
of course,
one.
that will be- I'm interested in continuum theories,
Okay.
right? That's a open for me.
Okay, so you're just cutting off.
But I
yeah.
put it at finite volume, spatial volume.
Mm.
That always gives me type.
No, it anyway is type one. To begin with,
To
it's
begin
type,
with,
if you
even
take
at
all the
infinite
bounded
volume.
operators, yes, all the bounded
No,
operators.
I'm not saying bounded, I'm saying I have the quantum field theory
Mm.
at infinite volume, like take five, scalar field theory, infinite volume, all operators, is that a type one?
No, to begin with, you need bounded operators for one and algebra.
Yeah.
Is that right?
Yeah, you need bounded operators for a polynomial.
But where in your definition?
See, even when you take when you take products of two operators, right, then you have problems. You have problems. So if your operator is, let's say, not well defined for some states in the Hilbert space, okay, then you take products of two operators, which may not be well defined for some states in the Hilbert space and some other states, then you will have a problem.
Sorry, please excuse me, sure.
No.
But does that mean, so what does that mean, bounded operators? If I try to take the theory in infinite volume, what about it? I have to put an energy cutoff.
Can you flash the
What
definition?
makes
So
bounded operators?
let me just go back to the definition.
There are two questions, the bounded operators and trace. These are separate.
Yeah, these are separate
So
questions,
first,
exactly.
let's solve the bounded operator.
But bounded
So this is the definition to begin with. So you have to put this.
So I missed the definition.
Yeah, just look at that.
Precisely what you
Yeah.
said. Operator is bounded if there is a number case.
If it has the largest eigenvalue.
Psi, A, this, thank you, Platon. And infinite over all such K.
Is operator known?
The infinite means what, sorry?
So you take the smallest k which satisfies it,
The smallest K is
which
the.
satisfies that inequality.
The lowest
So you-
number bound.
Take all the size and do O psi. And if you have the, if you have the norm of O psi is less than or equal to k,
K.
then you take the minimum of all those k's.
All the K, okay, so thank you,
You
okay.
call that the operator.
Okay, so this is bounded operators,
Yeah.
set of all bounded operators is D of H.
It forms an algebra.
And
Because
for-
under all these operations, the operator remains bounded. It was bounded to begin with. Okay?
But now it's not given at this stage that a sequence of bounded operators is.
We have not yet come to that.
In general, not.
Yeah, in general, not. It's
But
not
now,
possible.
just try to get quantum field
But
theory
you know,
even on
but that's it.
a finite volume space. You don't have bounded operators.
No, the field operator, that's exactly, so you just look
Maybe
at
that's
this
the
now.
only way you can.
See, this is always true.
We think that in this week's session,
This is infinite.
So this is.
So you
infinite.
have to
So you have to
smear.
smear, you have to smear.
Otherwise, you can't get going.
Otherwise you can't, and you have to smear in time. That's the point.
So you have to smear in time, sorry. Okay, so now let me ask you, but presumably not much depends on exactly how you smear, as long as you smear in some reasonable way.
Yeah,
So I take a quantum field theory, I put it in finite volume, I smear, and I take the smeared operators.
And now you take the bounded operators which are formed from those operators. For
And then
example,
you
like this.
take- Okay, now you take e to the I.
Hmm.
Okay, and these constitute all bounded operators.
You
And
can
then,
build up all bounded functions of phi will give you one function.
and the von Neumann algebra is the von Neumann algebra of all e to the I parts.
Yeah,
Hmm.
or any bounded functions of those.
Or
sphere
any bounded functions of these. Okay, thank you, so sorry. Okay, so now I understand that's what you meant by bounded. And your point is, okay, take the quantum field theory at finite volume, construct all the bounded operators. This is a form.
Yeah.
Type
One type
Type one
one. Next argument was for type one.
Ah.
That was about the existence of place.
Correct. Okay, this is von Neumann, but first of all, it's a von Neumann algebra. Secondly, it's type one, the claims at finite volume. That was, sorry, Shiraz, that was Shiraz.
Yeah.
And now trace, so now I understand, and it also therefore must have a well-defined trace.
Yes.
No, not therefore, I mean, this is not
It has the usual Hilbert space.
this particular thing, right? Not for any one element. This particular example has a trace for this time.
Okay, but what I'm saying is that finite volume, the claim is it's a type 1, right? Therefore, it has a well-defined trace.
Also infinite. If we take the full theory, but don't break it up into subregions.
I don't know about that.
Because I agree with you, because in what you said, I don't see why finite volume is coming in. Once you have
This is
bounded operators.
full bounded operators on the full space.
Okay.
Then that would be type.
How come you have a well-defined trace? It's still a bit counterintuitive. I mean, you have a continuum of states, right?
You have a continuum of states, but you do have density operators, and you do have your.
It's not really well defined.
If you take the full
Yeah,
take the trace.
Yeah.
No, that's what type. No, this type 1 algebra, the usual
I
Hilbert
was
space.
thinking that the finite volume part, in my mind, having smeared and gotten bounded operators, the finite volume went into a well-defined trace. But you say actually not even needed.
Yeah, not even.
Shiraz, it seems more general.
What?
Even infinite volume, the claim is there's a well-defined trace.
Wait, can I back up in for quantum mechanics? Okay, the trace, if we put this theory at finite temperature, the trace will be proportional to the volume. Right? Is that something you allow?
Apparently, there is some trace. It's not the continuum, it's not the infinite volume limit, is what I'm gathering of the finite volume trace.
The claim is that the claim is that the full space-time, algebra of the full space-time is type 1.
It's type 1, see?
Yeah, so I think then what must be type 1 when you're allowing only states of finite energy, not finite, but not allowing states of finite energy density. Because that clearly has a trace with a volume outside. And I presume mathematicians would.
But you need more than that, I feel, because if you take free theory in a box, and you count low energy states, the number is still V dqp, right? But there is some other, this doesn't have a good continuum limit.
But if you take this continuum limit, you will get states of finite energy density. So suppose you take states of finite energy in an infinite volume, that will have a good trace.
Everywhere finite energy.
The total energy is finite.
Yeah.
Not proportional to V.
What is the problem with finite densities?
Meaning there the partition function when we compute it is proportional to V. The trace.
No, but these states are normalizable. One is talking about the normalizable state.
Yeah, I mean it depends on what you want. If you're going to allow for the finite the density matrix at temperature T to be an allowed state in your theory, then that will not have a good trace because it will be proportional to V. But presumably if you allow only finite energy states, it will have.
In finite energy density states are sort of in a different sector. Right? That would be like the selection sector.
Yeah. From this weird way of saying it. I think of them as the same.
I feel it's more subtle to define that trace in an infinite volume.
Yeah.
Because you can take continuum state e to the I p dot x and make a very finite energy lump. Okay. And you got to tell me how to do a trace over those.
But that's
it's not related to V.
But what about just the Fock space trace? If I've got a finite number of particles, I've got a clear space in trace in Fock space. So if it's a finite number of particles, then there's no problem defining them.
Fock space.
Yeah. So I think the problems come with having infinite number of particles, or just like finite energy density.
Another thing to say is that
there you have continuum. You have a continuum. A dagger A is delta function. It's not quite so simple. I mean, usually we always put it at anyway. Go on.
those operators I think are not included.
No, but then you have to define the trace properly, right? It's not sum over P bra P get.
No, but if you put a wave packet for it, a smeared wave packet in Fock space, then it would be okay, right?
No, but there has
Based
to be
on the
defined
algebra.
Right.
there has to be defined the
But I feel it could be done,
if you
but not for a finite energy density.
I'm not there definitely, but even here because
Yeah.
we always go via the crutch of putting it in.
I agree. Okay, but I mean, you'd have the same question in quantum mechanics. Just quantum mechanics in non-compact space, you'll have the same issues in this way of thinking, right?
I don't think.
No.
Not for me. Because you have an infinite number of degree, you have an infinite number of quantum mechanical oscillator at infinite one.
Sorry,
anyway.
This one-level algebra is, this is a statement about algebra. It's characterizing algebra, right? Of bounded operators and so on. So from that algebra point of view, what is type 1? Without referring to what space it is acting on.
So from that algebra point of view, there are operators, positive operators in that algebra, which satisfies trace row equals 1. So there are density operators, and there are pure space. Yeah. So the classification is just basically based on the properties. Okay? So if you find an algebra which has the property that it has a positive density operator, such that trace row is 1, then you call it type.
I mean, a priori there is no, I don't know what density operator. I mean, it's just some operator. So you're saying some positive operator whose trace is 1.
Yes.
If I find you that,
Yes.
that would be type 1.
Yes.
Okay, but then what is the problem with 1, 0, just to take an infinite matrix?
Yeah, the problem
1,
which,
0,
the
0,
problem
0,
which,
0, 0, 0.
yeah, so the problem which happens, so that algebra will have a trace, okay? The problem that happens is.
No, I'm saying take infinite quantum field theory in infinite volume and consider this.
Yeah, but
consider
the
consider the
algebra
operator,
yeah,
which is 1 on the vacuum and 0 everywhere else.
But the point is you're talking about full algebra of the quantum field, right? You're not talking about an algebra in a subregion.
Yeah.
You have an algebra in a subregion, you have to
This is
find
addressing what they were saying.
Yeah.
It's no. I'm not making a distinction about whether it's a finite volume, infinite volume. Right?
No. I'm just saying, are you looking at a proper subregion of spacetime or are you looking at the whole spacetime?
Whole spacetime.
So if you look at the whole spacetime, there's no. That's what it is. You can find such operators. You can't find such operators if you restrict to a proper subregion and then you look for row operator in that subregion. In the algebra of that subregion.
Because this coming up with a positive operator trace 1 seems to be very easy because as I said, just write 1, 0, 0, 0, 0.
You're thinking of the whole.
No matter what I think about it, why can I just not?
You mean a row which is in that subregion?
No, but what are regions and so on? I mean, this is an algebra, right?
This
talking
is
about algebra.
Yeah, for an algebra, this is the definition. Okay. Now we are interested in algebras of subregions of space.
I think that there's an issue of whether this algebra admits pure states.
Algebra admits pure. What is that? That's part. What is an algebra admitting the state?
Which satisfies trace.
Yeah.
Rank
1 projector.
Rank 1 projector.
Yeah.
That's what is proposed.
Yeah,
1, 0,
yeah,
0.
that's what. So if it admits a rank 1 projector, then what
He
is
said, what's the problem?
Yeah,
with seeing a
infinite
rank 1 project?
What is this massive quantum field theory in infinite volume? What is the problem with just writing down projector on vacuum?
There's no problem.
There's no problem. That is a type 1 algebra.
But you can't do it for some types of problem. Like
a region.
Yeah.
Like a region, subregion, proper subregion.
That's why I was saying that even in infinite volume, this algebra has to be type 1 because it admits and rank 1.
Yeah.
Yeah. No, but what was this other comment that Shiraz made about the things going like volume?
Yeah, I'm saying that in infinite entry, if you are only interested in finite energy states, it seems to me that there is no problem. Okay, but we are often interested in computing a partition function at the finite temperature. Trace e to the power minus beta h.
What does this have to do with all this discussion?
Because we're trying to define a trace.
Okay.
So when do I want to define a trace? When I want to compute finite temperature partition functions. Okay, so I want to clearly compute a finite temperature partition function, trace e to the power minus beta h. Saying that will, for a mathematician, be ill-defined because it will sum over states of finite energy density. Because it will go like one.
No, but is that a bounded operator? The trace operator that you're taking is that a bounded operator to begin with?
But I'm trying to define a trace.
Of a bounded operator.
the minus
Eigenvalue, large eigenvalue is infinity, then obviously
it is the minus beta is bounded.
it should be bounded. Yeah, okay. Right.
And so, just so I understand, so okay, now I at least understand the case where you include all of space, space and say time, but now let's look at some region. Now, just to take a step back, in my mind, the essential point is that, when you're trying to cut that subregion out from the rest, you have local operators as the boundary of the region, but you have told me I have to smear them. So now, how do you define the smearing properly for a bounded region?
So
You can smear
you
it
smear-
down, perhaps along
You
the
just
boost operation.
Mhm.
So
And that is okay.
That is okay. You can smear, you can, so your functions of compact support will lie in the region in which you are considering the algebra.
Okay, and it's
And then you
enough to do that.
consider the limits.
You have an open set, so it's always possible.
It's always, so it's enough to, by smearing, you allow any functions of compact
Yeah.
support. That's good enough.
Yeah.
Okay, I got it. So it's like a one-sided smearing and that's good enough. So you can define the form norm in algebra for this spatial region, but it is not like operation. And how do you prove it or what?
Just from the properties. It's not, there's no proof of that. It's just from the properties. You find a polynomial algebra which has density operators and trace and all that, and you call it a.
No, what is the?
So the way these people, mathematicians proved this, the way they came across this was in specific examples of, infinite qubit systems. So even if you take an infinite qubit system, certain kinds of infinite qubit systems will not give you a type one.
I understand, but I feel it's
Okay, just coming back to quantum field theory, if I looked at the subregion, what is the proof? I mean, since you actually studied this, is a kind of proof that.
Okay, so just let me go to the next slide. So type one was something which is we just discussed now.
So type 1 is a algebra where you have a rank 1 projector or an algebra with finite case, or these supposed to be well continuous. Or both.
Let me think about that because you could have a finite trace. Yeah, I think it will be true.
But Shiraz just mentioned that it's not equivalent, right? Because in a massive quantum field theory, let's say, in infinite volume, you would have a rank 1 projector, but not finite.
Trace is not defined for every.
Not every 5 bound.
Every row.
Yeah. So these seem to be inequality.
I think type one is when you have at least one density operator.
Okay.
With your notion of trace. Then you would call it that. Okay. I'm sorry. And pure states, it also has pure states as well. But then if you can find density operators which satisfy this and you have pure states.
Suneeta, really sorry for all the questions. We don't have a time limit, so.
Yeah.
And you sorry, there's states where trace row is one are not by definition pure states.
No, row square should be row.
Oh, row square. Sorry, yeah. Okay. Yes.
Okay, so now let's go to type 2, which in which there is a renormalized trace which satisfies this trace AB equals trace B and this condition. Those are type. If you can come up with something, and as I just said, the mathematicians who first got these type 2 algebras, they did it in infinite qubit systems. Because you just take a system of infinite qubits, but you do certain operations on it, then you get a type 1.
So there is no density operator or there is no density operator with trace form?
No, there is no density operator in type 2 with trace rho equals 1 where this is a Hilbert space trace. But there is some other trace that you can define in the algebra which satisfies these properties and then you can find density.
And then trace that trace on row.
Rho will be 1.
And density operator means operator whose eigenvalues
So
are
positive or in positive
less than equal to
positive.
one, presumably.
Positive.
Any positive.
Yeah. Okay. Now you.
I mean, if I have a spin chain or whatever, any system, if I have, so it doesn't have pure state. Is that the point? I cannot even consider pure state.
Yeah,
Even
in type 2.
So in particular, the vacuum has infinite degeneracy or something?
I don't know. So the example that these people first came up with, that's a simple example. It's an infinite qubit system in which you do certain operations and then it doesn't have pure state, it doesn't have density matrices with a Hilbert space trace, but you can find the new trace.
But if I have
So
a
you have
vacuum, I can always project on that vacuum. And then I will have this density matrix, right? A projector.
Yeah, so let me just think why they
ground state degeneracy must be infinite.
Yeah, I don't have an answer for that right now. Let me just think about it. Okay, and there are
Maybe that has to go with pain or something like that. No, I mean it's type 2. This in particular that has infinitely degenerating ground state. Because I can always project on it, right? And make what the density matrix that is required.
So actually, the examples that we are all going to do are in quantum field theory, where you have some region of space-time. And then that's a type 3 algebra to begin with, and then you enlarge it, you do some things with it so that it becomes type 2. So in that space, you have to find an operator in that algebra which satisfies trace rho equals 1. Not the operators that you will think of will be operators in the full algebra.
No, I mean, if you take e to the minus beta h, which is presumably that algebra, I'm using it.
No, it should be an algebra where the operator is localized to that region.
Okay. No, I'm just taking the spin chain example. If I have e to the minus
So
beta
spin
h.
chain, I don't know what is the type of that.
Okay. No, I mean, you said that they construct example with some bunch of qubits. Right?
Yeah, infinite qubits, but that's a very specific construction. Okay, they're not just taking all infinite qubits.
Yes.
You have to take infinite qubits such that, they are entangled in a particular way and all that, and after that you build that.
It's an infinite collection of maximally entangled.
Yeah, maximally entangled. That will give you type 2.
Maximally with
Each, I mean, so you have take pairs, infinite number of pairs.
Okay, infinite number of pairs, and if they are not maximally entangled, then it becomes type 2.
Right. And you just
If
look
the
at
generic entanglement, it becomes type 2.
right, algebra on one side. You have an infinite collection of pairs. Just look at the algebra on one side. That is going to be kind.
Because for pure state, you have to do lot of work.
Doesn't it? On one side it doesn't admit.
so 1 is entangled with -1, 2 with -2, 3 with -3. Okay.
But what is I still don't understand. When you say the algebra acting anything, right? Any matrix,
Right.
why can't I not construct a projector? I don't understand. I mean,
Take this example.
yeah.
Take a lattice. 1 is entangled with -1, 2 is entangled with -2.
Oh, like that.
Okay. And now take the system which consists of 1 and I.
Okay.
So there's an infinite amount of entanglement between this and the left.
Okay.
So to make up your state, you'll have to do an infinite number of unentanglements.
That's
That doesn't lie in the.
We are talking about a particular matrix being infinity, right? But it's about algebra. We're talking about algebra.
I am saying, is it a property of states or algebras? I mean, if I just take a infinite number of
It's
qubits
a property of algebra.
of algebra,
Yeah.
so okay, then
For
suddenly.
example, we are going to find that in type 3, the fact that you don't have such a density operator means that you have infinite entanglement in it. And normally when you compute entanglement entropy, you will think that's a property of the state, right?
I agree.
There can be some unentangled states.
I agree.
But here you get infinite entanglement entropy for any state.
Yeah.
Right?
The density matrix has infinite entry.
No, this is a statement of the state, right?
But it will run all the way to infinity. So you'll have to do an infinite number of things.
No, I consider this acting on this semi-infinite qubit chain, an operator which is just projecting on the first qubit.
I have the same.
It's just an operator.
If it's a statement about algebra, then once you give me a bunch of qubits, I say, okay, my algebra are all the Pauli matrices and their tensor products. Now, if
No,
that
this is
not the
this
statement,
is not such a simple problem. Okay, that the problem of the infinite
there is
qubits.
no structure.
Yeah, there is more structure to it. I can tell you tomorrow.
Let's say a vector also acts on this vacuum a finite number of times.
Exactly, that's how they define the.
Yeah. You are only allowed to act on this vacuum a finite number of times.
Yeah, that's correct. That's absolutely correct.
Then you can't do it.
Because it comes with some stipulation like that.
Because you're going all the way up to infinity.
But then some other notion of
Like a boundary.
operators, because that is,
Yeah.
it's not that's what is probably
But I thought
unfamiliar.
we only wanted like some positive operator.
Again, Witten talks about it in his lectures.
So they do not finite terms. One have the property that trace.
But if you have finite, you can just divide.
You wanted a pure state, right?
Pure state, but I thought irrespective of pure state, you wanted to define a row which is a positive operator and that's finite.
Trace,
That you can
trace.
still do, right?
Yeah, you can still. That's
Oh,
how
it's
it's
that, right? Cannot define as a.
But not the finite function because it's a different connections.
But if they want
Not
yeah,
like
like, so it's at least some bits, then it will define.
that's I think written that's discussed.
We can define things.
Is not very.
Okay, so let me continue. Okay, suppose in type 2 I have a trace, this new trace, Then I can find positive operators with trace rho equals 1. So in type 2, if trace of the identity can be, normalized to 1, then we call it type 2 1. And if the trace of the identity is infinite, we call it type 2 infinity. And the trace is actually, this new trace is unique up to a rescale.
And trace identity equals 1, I sort of understand. Because you subtract away from identity.
Yeah, you subtract away from identity.
You subtract the vacuum kind of thing. But what does it mean that the trace of identity is infinity? So
no, this is another algebra. So if I find an algebra in which the trace of the identity is infinity, but I do have such a trace, then I call it type 2.
I see. So it's like saying that the trace of the vacuum in that state is infinity.
The trace of the trace of the identity.
Yeah, okay. I see.
What is this subscript infinity or whatever?
Yeah, that's what I just defined, right? Trace of identity is infinite, then I call it type 2.
Oh, so in these examples you tell us about, that's the
Given the definition.
type to infinity.
Yeah, that's type
Infinity
2.
means trace identity.
You find a trace, it's either finite or infinite. If
Yeah.
it's finite, it's type 2 1.
Yeah.
So I thought if you have a trace which is finite, then it's type 1.
Type 2 1. No, this is a new trace. This is not the Hilbert space trace.
Oh, okay.
So in type 2 algebras, you have a new trace, which satisfies trace AB equals trace BA. And trace of some positive operator is greater than 0. And then you can, using that trace, you can define these traces.
Is there some standard example where we know a new trace?
Yeah, that is that qubit system.
Okay.
That was there in the
new trace-
original paper.
Okay. And if the new trace in that qubit system is?
The new trace in that qubit system is one where you take the trace only over a finite number of the qubit pairs. Although the total system has infinite number of qubits, you take it only over a finite number of qubits. That trace is this example of this kind.
It would suggest that in any theory we can find a new trace over some finite subset of degrees of freedom.
You could
And make
construct
it that too.
any theory, I don't know. In the qubit system, I know how they calculate it.
That is 1, you are saying?
Type 2 1 is when the trace
Yeah,
of
no, in this qubit example, is it type 2 1 or type 2 infinity?
That's type 2 1. Yeah, type 2
With
1.
this new trace, I think.
Yes. And then type 2 infinity is just some kind of a direct sum of a type 2 1 with a 1 infinity.
I'm having trouble understanding this type 2 1. You see, you take an identity operator and you get trace 1. That
Integral operation.
I think you have to divide it by.
You have to divide it by that whatever it
You
is.
can scale the trace.
finite.
Yeah, finite.
Yeah.
One means finite.
Okay, so then in that case where you have the type 2 algebra, you can define a quantity minus trace rho log rho, where this is again your new trace and your rho is again your rho which satisfies this equation. And therefore you can define something like an entropy for that algebra.
So it's like, is it like that in the example you have this infinite entanglement of the state? So if you build the algebra somehow put on top of that, then that's like you're seeing all this infinity. But when you're using this modified trace means you kind of remove all that and just work with these finitely many poly operators acting on this, and then that would be more better defined.
That in the particular qubit example, that's true.
So what you were calling the new trace, now you're calling renormalized trace.
Yes, that's a renormalized.
The UFT in some subregion that will be 2 1.
No, it will be type 3 to begin with. And then we have to do some things to make it type 3.
It's more gravity, right?
Yeah, you have to include gravity into it to make it.
So if you take a normal trace has the property that you take a positive operator and it has a positive trace.
Yeah, that is a
That is
part of
true.
the, that's the, I just sort of. This is the.
I see.
This is true. Yeah, this is true.
I see.
Okay, so now if you have the trace, you have the density operator, you define something called the entropy of the algebra. And if you are in type 3, that means that there is no renormalized trace and no density operator in algebra. And the quantum field theory in a proper subregion of spacetime is a type 3 algebra.
And so can you give us some intuition for why this is true, that you cannot define a renormalized trace in a finite region?
You cannot define what a renormalized trace in a finite region.
Theory in a finite region. That's what you said.
In quantum field theory.
Yeah, quantum field theory.
In a finite.
Somehow the entanglement on the boundary has something to do with it. That's
See, the fact that you can't is associated with the fact that you have a infinite entanglement.
But I thought about if I subtract away, I choose some state, I take differences between two entanglement entities. Why don't I?
Yeah, that's fine, but she wants to define an entanglement.
Even in that example, the entanglement entropy was infinity.
Yeah, and then you took a difference.
Yeah,
See, if your qubits are not, just take the qubit system. If they are not maximally entangled, then you don't have that.
I see.
Whatever you define as that trace in that qubit system which are maximally entangled, that will not be there if they are generically entangled.
So why give me some intuition for why is that?
Sorry, I wanted to ask this. So if they're not maximally entangled, you don't land up in type 2 situation. It's just type 1.
You have type 3.
Oh, you have type 3.
Yeah.
It's worse.
You don't have this new trace which you have. You don't have that if you have generic entanglement between the qubits.
I see. So it's not so directly because you have too much entanglement. I mean, intuitively, even less.
But you see that, right? Because you see when you have type 3 algebra, you have no density matrix. So if you take a density matrix that you normally construct and you try to do minus trace row or row, you will get infinite. Okay. But normally the entanglement is infinite only in a state, right? The property of the state. Here it's a property of that because it's true for any state.
Is the point here that an excitation, even if I try to bring an excitation around the vacuum, if it's local, completely localized, that will change the entanglement entity by an infinite amount? No.
No, that is a very UV thing. You make some finite excitation. In fact, that's why when you compute differences.
Yeah, so then what is the problem? I can't understand why there's a problem.
Because you can't take the cutoff because these are purists. You can't take the cutoff to 0.
I think the point is that
You just can't define it.
you want to define something.
No, you don't know how to define the limit.
Yeah, you don't know how to. I think you can't. It's a subtle thing, right? Given an infinite object to try and define something finite. I don't quite know the type 2 example, but I'm just saying.
Actually, I'm going to give you an example in the quantum field algebra itself. Once you extend it, I'll show you what the trace looks like. And then it's possible to prove that that satisfies all the properties of it.
I mean, the fact that it's failing even for a non-maximally entangled system tells it's pretty subtle.
Right? The point is that you want to define something like a trace of either minus type in the beta y to 0. Because that would be a natural notion of trace. But the problem is that if you're in a type 3 setting, this h is the natural h is the boost operator. And the boost operator has a continuous length. You can't do that. In the type 2 setting, you're sort of in a happy coincidence because the state is maximally entangled. So h is like the identity of it.
Yeah.
So there it's like a coincidence that you can define that object, that child going to 0. But any other situation, the spectrum is continuous, so you can't. That's roughly the equation. Is this fair?
Yeah.
Well, the trace will become.
So, but suppose I had it on a lattice, I compute the state, and I take a limit.
No, on the lattice, there's no problem.
Right.
But lattice, it's type 1.
Right, I understand. But then I take a continuum limit. Okay, I'm trying to understand if it's a real issue or is it an issue that we haven't yet learned how to define an algorithm, how to define a limit, or it's a real physics issue.
If you put it on the lattice and you take all states and you take differences in entropy, everything is true.
And then you take the limit. You take the continuum limit.
Everything is fine, totally fine. Okay, you can show everything.
So it's only a matter of learning how to take a limit problem.
Yeah, but it's a matter of if you want to be a purist and you want to preserve Lorentz invariance every step of the way, then this is an issue.
Okay, but I mean, in pre-calculus days, you might have said that things that are defined by limits are not really well defined. We're very happy defining things by limits. Okay, so if this is some limit of something, why should I be bothered? Where is there a real distinction?
I will be bothered only when I'm solving things like GSL, where you have manipulating quantities where there is some expected relationships between those quantities, but each of those individual quantities is infinite. Yeah.
I do want to take. If you want to do ordinary quantum field theory, any system you run, bother. But if you want to do gravity, especially, you want to preserve causality, you want to ask delicate questions about inside the light cone and outside the light cone and so on, then I think it's fair to say you need a set like that to be sure. See, you can't do gravity on the lattice, right? I mean, well,
the problem is that you don't know how to regulate gravity.
Yeah,
that is the problem.
Yeah, that's the problem.
Okay.
Like in string theory, I mean, Ashok often says this, right? You don't need any regulator, the answer should come out to the area of it. We don't have to do that.
Yeah. No, but just about the statement that quantum field theory in a region, you cannot define a trace. That sounds like an extremely formal statement.
It's very formal. On the lattice, everything is fine.
And lattice, everything.
Everything is fine.
Everything is fine, and there is no problem when you take the limit.
No,
Yeah, there's no.
for differences.
Yeah.
But yeah.
Meaning one state and the other.
Yeah.
But suppose I want to manipulate individual quantities like the boost energy and the entanglement entropy, and I want some, there's some relation between them. I want that expected relationship to be true when I renormalize each of those quantities, right? That's where I will have an issue.
You're trying to ask questions about algebra, right? Not whether a given number is well defined. That's what this classification is. So now we have asked the question in terms of algebra.
But I'm trying to understand whether there's a physical issue. Yeah, I mean, is it not possible, really speaking, for in a region to define a trace? If you can define it through a limit, I'm happy, because I'm happy with calculus, right?
But now you have two quantities. You have
It's the standard renormalization. There's a UV divergence. I mean, it's really as simple as this. We know there are UV divergences in quantum field theory. We know how to regulate them on the lattice. You get finite answers for everything. And the physical answers are suitably renormalized.
Okay, but I take your point that you can't easily work with this limit.
Yeah.
So you want something better to work.
Yeah.
It's a fair one.
Especially for like stuff inside the horizon, outside the horizon. I mean, you need something. Right? You can't say put the system on the lattice.
I mean, usually, like,
I think it's
like these original calculations of such kind of they were done in some ad hoc regular, some regulated, they did some whatever hardball cutout, they get some divergence. Then you show that divergence cancels with the divergence. So here you don't want to do that. You want to strictly work in
Okay. Once we get to gravity, there are a whole new set of issues. But let's just focus on quantum field theory there, because that's where this statement is made. Right?
No, but if you want to do GSL, you have to include
GSL,
right? Area by 4G plus.
There is area over 4G.
Are you saying just for the entropy of the field theory in space, right?
Yeah.
Okay, but for a moment, suppose there was no gravity at all. Okay,
Yeah.
I just had quantum field theory.
You don't need
Just to clarify that
You
situation.
don't need it.
Then it seems to me it's a matter of technically defining it.
Absolutely. Once you put it on the lattice, you can compute trace row log row. You get something going like 1 over the lattice cut off to the appropriate power. If you look at any finite excitation and compute entanglement of it, it will be this universal part plus corrections, right? You subtract.
And in fact, like these examples that Nati considers this fractals, etc., which are where there is the issue.
Any local quantum field theory.
Renormalize, coming from the lattice first and then taking continuity.
Renormalizable.
So there are issues in doing all that there. So there maybe it can be sharpened.
I'll say again, please.
I mean, if your point of view is that once you have lattice and then you think of continuum limit, then everything makes sense.
Yes.
In theory, it's for the continuum limit.
I mean, take a local.
Yeah.
Okay. Okay. Or even in an effective field theory sense, I would even say you can make. I mean, for me, the entanglement entropy, if you thought about any effective field theory, is well defined in the same sense in which every other potentially UV divergent quantity is well defined.
In fact, I feel we probably need to put counter terms on the boundary.
Which are called area over epsilon.
Yeah, okay.
So, exactly. I mean, everything matches the usual thinking of, everything is finite, everything is the universal counter terms and so on and so forth. But
Fine, you get it.
Yeah. No. Yeah. But also, it is really interesting. I mean, what you said, that the type 2 example works in this one case of maximal and otherwise there's so much structure to both setup, right?
Yes, both different. Okay. So in order to define the entropy for the algebra, it must be type 2 or type 1. But there is a mathematical construction called the cross product by this modular automorphism group, which extends the original algebra such that it becomes type 2 from type 3. And then, of course, you can define things like the entropy of algebra. So
Okay, you'll explain this.
yeah, everything is going to be
Cross product.
So let's start by understanding this cross product construction. So we enlarge the algebra by adding an operator, and we enlarge the Hilbert space to get states on which this extra operator acts. Now let me just explain it in the setting in which Witten did it, so that we understand what quantities we are dealing with in this situation. So you have a low energy effective field theory of quantum gravity. So you have a matter QFT, you have gravitons. And the algebra of fields, as we have seen in the right exterior or the left exterior, is type 3. Okay. Now we are interested in this theory in the G going to 0 limit, keeping the horizon radius space. Then what Witten proposed was you add one more operator. Okay, that operator that you add to the right algebra was just quantum field operators. Now you add this ADM Hamiltonian to the right algebra, and you add the ADM Hamiltonian to the left algebra. And then what he did was he said that you have to next implement this particular constraint. So this constraint is what? This constraint is that you take the generator of the Killing isometry, which is this operator H hat, and then you impose the constraint H hat is equal to HR minus HM.
What did you add to the right?
The right ADM Hamiltonian.
Oh, you added the right.
Yeah. So what we are now doing is we are enlarging our theory in such a way that we allow fluctuations of the right ADM.
And to begin with, what was the algebra without?
The algebra was just the quantum field. The quantum fields included gravitons.
So in the beginning, it didn't have HR or HL.
It didn't.
Either one.
Yeah, it just
And
had
now we introduce HR
as a new operator.
as a new operator, and also we define HL by this thing.
No. We introduce HL also in the algebra, left algebra, and then we implement the constraint that H hat is HR.
That's equivalent to saying that HL is defined by subtracting H hat from HR.
Yes, that's. So this is my H hat. It is the generator of the Killing isometry. And we know actually in Einstein gravity that H hat is HR minus HL. And now you implement this as a constraint. Okay. So you add, more precisely, you add the operator HR minus some initial mass of the original unperturbed black hole, so that you have a finite answer in the G going to 0.
Sorry, S was what? That surface S is the horizon?
The surface S is a Cauchy surface for the entire space, full space.
Okay.
Suneeta, I just missed 1 minute. What did you say before? You add one operator and then what?
Yeah, so this is the cross product construction. And I'm just giving the example where it is used directly rather than the mathematical definitions, which I will come to later. So what you do is you have the right algebra and the left algebra and the Schwarzschild case, in the classical case, right? So you add the right ADM Hamiltonian to the right algebra and the left ADM Hamiltonian to the left algebra, and then you implement this constraint. That H hat is HR minus H.
And sorry, H hat is just by default.
H hat is the generator of the Killing isometry because V is the Killing, the D by dt.
So what operator have you added? Sorry, this HR and HL.
HR and HL.
So, but you also implement this constraint, so you've added only one more.
Yeah, you actually added only one.
Nice.
Okay, and we have to also expand the Hilbert space so that the HR and the HL can act on something. So you take the quantum field Hilbert space and tensor it with square integrable functions. So you can think of them as square integrable functions of HR or HL, or you can think of them as square integrable functions of the conjugate variable, which for the left Hamiltonian would be the left time and the right Hamiltonian would be the right. Now you know that there is a time translation symmetry in the space-time under which the left time goes like this and the right time goes like this, because the Killing vector is oppositely oriented in the right and the left sides. So you can actually choose, this, you can fix one of them to be 0 by this symmetry. So effectively you have only one more new degree. Okay, so if you want to make it a little bit more precise, then you will start with the operator HR in the right algebra, the operator HL in the left algebra, and you will have a tensor space in which you have H times square integrable functions on the left and square integrable functions on the right. And then you have to implement the constraint H hat plus HL minus HR equals 0 on the Hilbert space. Yeah.
What are these square integrable functions?
So these are square integrable functions either of the Hamiltonian or of its conjugate variable, which is the time.
Sorry, why did you add this square integral?
So we want to allow for possibilities where the idiom Hamiltonian changes in a process. So you want to enlarge your Hilbert space. Yeah.
You want to
So the idiom Hamiltonian, you allow it to fluctuate. You just have it as a new degree of freedom.
I see.
So this Hilbert space is on the full Cauchy slice?
The integral, which I
The
wrote.
H part is on the full slice or the half? Slice?
No, full. Everything is full. So I have enlarged it to include the, this L square R on the right as well.
Is it like adding some like you are adding a boundary to this full slice?
No, you are adding the idiom Hamiltonian on the left and the right, which are defined on the boundary. You are allowing them to fluctuate in a process.
I was asking about this L2R part. Is it something like something?
It's a time on the boundary. The boundary right time and the boundary left.
So how does HR and HL act on these L2Rs?
So HR and HL act on the L2Rs. So let me just write it here. So if you call say HR is equal to some Q, okay, then you can if you write HR is equal to Q, then the way the other conjugate operator acts is minus IT by D. They have a non-trivial commutation relation. Just commutation relation between Q and T is I. And that's important.
These fluctuations are not the fluctuations of quantum
field. These are not the fluctuations of quantum field. They are fluctuations of the idiom mass. Yeah, the quantum field can fall across the horizon, for example. Now, to implement the constraint H hat plus HL minus HR equals 0 on the Hilbert space, the only way you can actually do that is by saying that a state is equivalent to another state which differs by C times phi for any state phi, where C is the constraint you want to use.
This is the enlarged Hilbert space.
This is the enlarged Hilbert space with both the pieces in it to begin with. Then it can be shown that considering this equivalence class is the same as removing one of these things. Okay? So that's why you just forget about the right Hilbert space and you just consider this to be the extended Hilbert space, H times square integrable function of that. And next we have to choose the operators in the extended algebra that commute with the constraint. So we implemented the constraint on the Hilbert space. Now we have to choose operators in the extended algebra that commute with the constraint.
And then, sorry, can you give some intuition for why you're adding this HL, HR? I mean, why didn't I add something completely different?
Okay, so let me just, the answer to that only comes from the fact that you will make your type 3 algebra to a type 2 algebra.
But just to ask, I mean, what is the rules of the game? You add something to your original type 3 algebra.
What you added is something very specific. You have added something very specific, which is going to make the type 3 into a type 2 algebra.
So
you cannot just enlarge. The cross products are not defined that properly yet, but it's not just enlarging the algebra. You have to enlarge it by something very specific.
And so just one thing, I mean, intuitively, so sometimes people say, oh, you had this, one quantum mechanical degree of freedom, and then you only ask about the observables pertaining to this degree of freedom you added. So it's in a sense, it's become a much simpler system, and you can make sense of it.
Yeah.
But thought of that way, maybe you can always do it, just add one, I can add two.
No, you cannot. If you want to make the type 3 into the type 2, you have to add only this. As it turns out.
Okay, so it's somehow, it's more than just, made it simple.
Yeah. Now you can ask if you just take the full quantum field theory, quantum gravity theory, then what will happen?
If I was a semi-classical gravitational physicist who knew nothing about algebras, would there be something natural about adding these fluctuations of HL and HL?
Yes.
Can you say what?
Yeah. So actually the thing is, if you believe that this constraint should be implemented.
Which constraint?
The constraint that this H hat plus HL minus HR equals 0.
Which semi-classically is true, yeah.
Yeah, so you want to implement this. Okay?
I want to.
So now if you want to implement this, then the cross product follows naturally. It follows complete, and I'm just going to explain that.
Okay.
And then please go on.
Is there a discussion about this gravitational Gauss law, right? That's what, all this central discussion that you were having, that somehow contributes to this infinite entanglement, right? So I guess the statement is that the infinity that you are seeing at the midpoint, where these edges intersect, as just a quantum field theory. You want to now interpret it as entanglement coming from these various sectors in the theory, having to do with different charges, but they are entangled. So you are adding this extra degree of freedom to interpret that infinity as coming from somehow the center part of this kind of Gauss law part. Is that
It could be, yeah.
correct?
Or maybe you're allowing the horizon to fluctuate or what? I mean, something you're doing here.
You're allowing the idiom mass to fluctuate.
You're allowing the ADM mass to fluctuate.
You're not in full quantum gravity. You just added this new degree of freedom.
Yeah.
You're allowing that to fluctuate.
Right. But in an intuitive sense, at least, and I think it can probably be made precise, but anyway, if you were keeping all the energy in the gravitons outside anyway, and measuring the ADM mass, then the extra thing you were missing was the sort of black hole mass, So one way or another, you're allowing to keep that. Perhaps that's what's. I mean, what is this very? Let me ask just one more thing. Suppose I also introduced another semi-classical observer in the middle going along, and then I said I want to keep track of that guy and your ADM mass, and now I have two L2 worth of degrees of freedom. Could you have gotten a nice L2 that way?
You can add more degrees of freedom. You can add, for example, a rotation at infinity. You can do that, but that will not change the type of algebra.
It is because of this entanglement, right? That is crucial. I think this constraint that is being implemented, right? If we just have one observer going like this,
that won't do it.
That won't change.
But you have to do this, and then you can do more things.
Yeah,
so this
you
is
can
like
add more.
the crucial.
You can add more things.
This is like the crucial thing.
But why is freeing out these Hamiltonians, allowing them to fluctuate? Why is that curing the infinite entanglement?
You're asking physically why that.
Yeah, I mean, just some words I can sort of see.
Very comfortable.
Yeah, it's not very obvious, but the thing is only this works. And I'm going to just explain to you why. Only this works.
Yeah, as in this is absolutely right.
This is the operator you should be adding in order to get the desired outcome.
How is that constraint equivalent to that equivalence relation?
No. So you have to implement the constraint on a Hilbert space. Okay. So the way if you look for states which are annihilated by this constraint, there are none. So what you have to do then is to identify every state with state plus c times some other state. This equivalence class, you consider this equivalence class, this amounts to just dropping one of the L square half. Okay, now we have to do the second step in the implementation of the constraint, which is to get operators in the extended algebra that commute to the constraint. But before we do that, we pause to note one fact, and that's the important fact here, that H hat is a special operator in the QFT. It's the modular Hamiltonian of the QFT. And that's going to be very important in what follows. So whatever you added and whatever constraint you implemented, those are very crucial. So let me just quickly in one slide explain the modular Hamiltonian. I'm sure most of you are familiar with it, but let me just run over the definitions once. So in a QFT, the cyclic state, or in any Hilbert space, the cyclic state is a state which is such that A psi for A in the particular algebra that we are considering is dense in the Hilbert space. And it's a separating state if A psi equals 0 implies that A equals 0. So now what you do is you take such a cyclic separating state in your Hilbert space.
Although many times this has been explained, please excuse me. So you take any state psi.
And you take an algebra,
take
a special state psi, take the algebra of whatever algebra you are interested in,
right?
And if A psi is dense in the full Hilbert space.
Just explain once what that means. That means it can be obtained as the limit of states in the Hilbert space.
Most of the states in the Hilbert space will be given by this form A psi.
Right, okay. For A in the is dense. Oh, I see. You mean you take one state psi and then you
operate with all the algebra operators.
And that should more or less give you the whole Hilbert space. Okay.
Which we know that in Minkowski, we know that the Riesz-Leiter theorem tells us the vacuum is such a state.
Okay, got it.
Why not all the states? Why not all the states?
No, the cyclic state definition is you take a special state which has the property that if you operate with the algebra on that state, then that's diffeomorphism. It's a property of the state.
But you're saying you can't generate states like sharp, weak states, which are like poles.
No, every state will not be cyclic and cyclic.
No, I meant like I thought the question was why can't we generate all states by hitting with A? So I think the holes are where you have these states like sharp, weak states, which you can't create by hitting it with finite.
Yeah, actually, basically, if you have a localized algebra in a region, right, you want to create all the operators in the Hilbert space by acting with A on its side. So that has you have to show that there exists such a state,
Yes.
because it's not obvious.
Yes.
Yeah, so if you get most of the states by acting with A on side, then you call the state cyclic. It's separating if A psi equals 0 implies A equals.
But also, so here QFT is the QFT of fields outside the horizon.
Yes, it is going to be.
And
We are going to, this is just a general definition, but we are going to apply it to fields outside.
and the script H you wrote before is the state.
That's the phenomenon. Script A is a phenomenon.
No, script H is the Hilbert space of this QFT.
Yeah,
And L2R is like
and added
inside the horizon.
new added for state.
Yeah, but it's supposed to be like degrees of freedom inside the horizon, like some standard.
No, it's just time. L square R is not that. L square R is the area mass.
Okay.
Now you define something, some operator called the Tomita operator, which is associated to the state. And it is also associated to the algebra, such that if the operator acts on A psi, it makes it A direct. And this is true for all the 8 algebra. And you can easily see that Si square is 1, so Si is invertible. And there is a unique polar decomposition for this operator, where this delta psi to the power half is positive.
Presumably, since we're all constructed, you can construct such an operator.
You can construct such an operator for example, for a finite dimensional Hilbert space, you can easily construct. Okay. Now this del psi is, if you write it as e to the minus h, then this delta psi is called the modular operator and h is called the modular hammer.
So it is
Yeah.
class parts.
Yeah. This
So
positive operator delta psi is,
that follows from
so you can write it as just e to the minus h, and that's the
or
modular.
define h to be the model.
Now the important thing about this modular operator is that this modular Hamiltonian generates automorphisms of the algebra. So this H is not actually part of the algebra by itself, but it when it acts on the algebra operators in this way, it keeps you within the algebra. Now the important thing is,
Sorry, slow it down. So, okay, this is an automorphism.
Yeah.
So this, what does that mean exactly? So that
It exactly
it
this.
gives you back something in,
The same
but
algebra.
it gives you the whole algebra. Is it
No,
an
it will not give you
automorphism?
some more. You could act on it with different operators in algebra. You will stay within it. That's all.
So that's all it means.
Yeah.
Okay.
Yeah, I was spacing out. Sorry, you chose some state, is that right? At some point?
Yeah, I chose a cyclic separating state and used that to define the modular Hamiltonian.
Define the modular Hamiltonian
It's supposed to be inside.
making density matrix out of that state?
Yeah, exactly.
Is e to the IHS like some?
Just one minute. Just we see what is the cutoff time. Tell me now, because it's already going to be 1. You tell me, whenever you want to stop, we stop. And we continue this.
Whenever is an actual stopping point, because there's a topic.
Yeah, so let's end up at some natural stopping. Okay. So the statement is that this operator creates automorphisms of this algebra, and that's this precise state.
So this is one-sided modular Hamiltonian.
No,
Modular.
No, it is a full two-sided.
It's full two-sided. Yeah.
But of course, it's trivial for the, you see, if the modular operator were to factorize into a part belonging to the algebra and the part belonging to the commutant,
Yeah.
then the
It doesn't
commutant
act
part will just stand
Right. So if I'm interested only on the right-sided algebra, it acts as if
It is
being acted
as if
on
it's
the
one-sided. Yeah.
one-sided.
But I can define this modular Hamiltonian even for those algebras for which the splitting into the left and the right is not there. So for example, in type 3, if I have this modular operator, it does not factorize into a piece from the algebra and a piece from the commutant. It does not factorize like that, but even there I can define
But
this.
in this case, for example, so usually people don't like this because it has this divergence.
Yeah, the divergence is not
So
there because we are considering the full.
Yeah, no. So no, I mean just to think of this as we said, I can think on also as let's say the right-sided one.
Yeah.
Because it is not active. If I'm just interested in the right-sided one.
Yeah.
So can I just try to address what Shiraz was saying? Why is it that introducing such a thing would cancel the divergence? Because this itself is kind of divergent and is exactly the same type of divergence
The one-sided
that is coming from
modular.
the entanglement
But
here,
if
right?
you introduce something like Minkowski-Hamiltonian, you have that object integrated over the entire quotient size. But that's
I'm not going to split it up into product of one-sided.
No, just try to intuitively understand why.
Yeah, I'm not going to split up. I'm going to do every construction with a full one whenever I'm doing a type 3.
I mean, the thing is that if you include the boost going up one side and the boost going down the other side, that's like you changing Minkowski slices. That's completely nice at the splitting point.
Only
So
if you have a discontinuity, like you do one, not the other.
no, then you don't. But here you're going to construct.
Yeah, I'm going to do
which
it.
are smooth, right?
Yeah.
I mean,
Right.
Whenever I'm going to talk about type 3, I'm going to talk about the full.
So that's kind of the point, right? Like because in type, as Naveen said, in type 3 algebras, the modular flow is an outer order. Whereas is it true that in type 2 it is inner order?
Yes, in type 2 it is.
That's what you're trying to do, right?
Yeah.
You're taking in outer order.
Yes, I'm trying to make it in.
What is outer?
yeah.
Outer order are generated as blind. Whereas inner where it lies.
H does not lie in that.
H doesn't lie,
In that.
but anyway, after exponentiating, it's an automorphism.
But
That's
The
a not
other
really-
case, H itself lies.
yeah, so you're making it into an inner by introducing the adaptation. That's what you're doing.
Yeah.
Yeah, like this. So yeah.
Yeah. So this H, what I got was that you chose some abstract state, and then
Not abstract, cyclic separating state. Yeah.
but I mean
some
you
abstract-
that's quick state.
Yeah, I'm not told.
And then you
You can, if you had 2 or 3 such states, you can define an H for each of them.
okay, but I'm getting confused about this discussion about how it relates to boosts and so on. If it's some state, how do I know what it relates to?
No, boost will be for a particular state.
I mean, if it's a Minkowski vacuum and you're looking at it on
And
one
if you're
side,
looking at the modular
Then-
Hamiltonian associated to the Minkowski vacuum,
Ah,
then that is
That's
like a
assumption,
boost.
right?
and then you know if you then there's a natural nice operator,
Yeah,
which is the boost, full boost.
yeah, full boost.
That's all.
but which state are you going to choose that will
I'm going to explain that. I'm going to
Okay.
So, but for every cyclic separating state, you can define a modular operator.
But also, I think even if the state was not, even if the state was a slight deformation of the modular state, modular flow very close to the bifurcation. So this would still look.
Will still look like that. Okay, so let me just answer the question here. The operator H hat, which we had in Witten's construction, is the modular Hamiltonian associated to the Hartle-Hopkins state of the theory. And this operator, therefore, generates automorphisms of the algebra. Okay, now let me just show you what is the cross product. So the cross product algebra is the enlarged algebra where we have added this extra operator. And I have just put exponential of that operator just to show you that they are bounded.
From the purest point of view, I guess one needs to prove all this, right?
Prove all this in a sense, cross product, whether the cross product leads to a type 2 theory, that you
Yeah, that adding this particular thing.
No,
is
so
the required.
the theorem
opportunity.
actually says that if you take the cross product with this modular automorphism group, then it becomes type. Not if you just take some
But how
arbitrary.
is a modular? Achha, so just you construct the Tomita. There's an abstract way to construct the Tomita operator.
So you know what the Tomita, what the modular Hamiltonian is for this Hartle-Hopkins state of the theory. You have to do the construction with that.
Yeah, I got it. But actually, probably just to begin with for the Minkowski state in flat space, right? The boost is the
Boost is the
That has to be
modular.
proven,
Boost
but once-
operator is the modular.
that has to be proven once, but then
Yeah, that's
easy.
easy.
Okay.
Okay, so the cross product algebra, let's take the left algebra. So you have these operators A prime in the left algebra. Now what you do is you dress them with respect to this modular Hamiltonian. You dress them like this, and this dressing, this TL is exactly the left time. So it is the object which has a non-trivial commutation relation with HL. So you consider only dressed operators. And what's the advantage of doing that? So you can do the same thing to the right algebra. And we call that
EL is an operator here or?
TL is the conjugate variable to HL. They have a non-trivial commutation relation, which is very crucial.
What is M0?
M0 is some basic mass of the black hole before anything fell into it.
It's just
We will start with that. It's just
a number.
It's just a number, and you put it there because in the G going to 0 limit, you don't want to have a divergence. Okay. G Newton's constant. So this is just this is M0. So M0 is just the horizon radius divided by G. Horizon radius is kept fixed when G goes to 0. So now I don't want a trivial divergence in the limit that G goes to 0. So I subtract out by this mass. So I'm allowing fluctuations in the alien mass space.
So the state that you consider is a vacuum, etc., that I should think of as a boundary state or a bulk state?
The vacuum, it's a
This
vacuum.
cyclic separating state.
Yes, it's a
over
cyclic
which you make
separating
this
state for the quantum field here.
boundary theory.
For the full quantum field. For the quantum field here, yeah, by the bulk. I'm not doing anything with boundary algebras. I'm doing everything with the bulk. I'm taking asymptotically flat. You can do it for radius also. You can look at boundary algebra, but I'm not doing it. Now this TL is the conjugate variable to HL minus H0. So and minus M0, and that's your construction. You rest the algebra operators and you add this new. This is the cross product. This structure is called the cross product by the modular automorphism group because this H hat is the modular Hamilton. And the theorem says that the resultant algebra is type.
Can I ask you something? I mean, if I were a very simple-minded person and I was thinking of gravity in the alien formulation, then the A prime operators would be, for example, graviton wave packet, creation operators of graviton, say on the left or right? And they wouldn't commute with the constraints, with the alien constraints.
Yes, they wouldn't commute with it.
Is this a way to
make them commute? Yeah, that's actually the last point here.
Okay.
You see that these rest operators commute with this object. Why? Because, well, H hat has a non-trivial operation on A. And so when you take the commutator of this with H hat, you will get something. But HL also has a non-trivial commutator with this operator because of TL. Okay. So the two will just cancel out each other, and HR is of course something which commutes with all the length.
So I mean, in simple-minded way terms, is this just saying that you try to create a graviton wave packet in the right, you didn't account for the fact that that would have changed the total ADM mass, so you didn't end up creating
You didn't account that, yeah.
Now you're accounted for that. Okay, great.
Yeah, but the point is that this
just makes it sort of intuitive why it's a reasonable thing.
Yeah.
What
so
is
now
H hat again? Sorry, what is H hat?
H hat is the modular Hamiltonian.
Okay,
It
full
is
quantum.
also the generator of the killing isometry in this case. Okay. Now the thing is, you see, you wanted the operators to commute with the constraint because that's how you implement the constraint on the algebra. Okay. Now you do that, and what you do turns out exactly to be the cross product by the modular. So that exactly makes your algebra type. You couldn't have just added anything.
Okay, but this makes it more understandable for me. But I mean, I'm just saying that I would have, if I were, a sort of pakka person who believed in quantization, then I would say, okay, allow me to do ADM quantization. You didn't start with a set of physical operators in the first place because they had to meet the Gauss law constraints.
Yeah, they have to.
So you just didn't have a good algebra. You just have a good algebra now.
But it turns out to make it type.
And then somehow,
because it's a modular.
Gravity is clever enough. If you start with a good algebra, then it has a generalized notion of trace. And this is always the case. You have some algebra which commutes with the gravitational constraints, so I would declare this.
Yeah, so actually I'm going to do some discuss some more general construction tomorrow, where you get exactly that by including gravity, not even just implementing a constraint.
So why don't you ever had operators which had positive energy on this side, negative energy on that side? Meant to this total, total constraint, not change the energy. The
One side.
one side.
I mean, I was thinking here that she's doing for ALs.
AL, AR, the same story.
So physically, how is this commuting with the constraint? Physically, how is this commuting with the constraint? Because if
I just showed you.
if you have things creating on the left side, let's say,
See,
how do you matching it on the right side?
it doesn't commute with H hat. Because H hat is a non-trivial operation. That's H hat doesn't commute with this.
Then you should be.
But the commutator of these two cancels out.
That seems to be the intuition. It's a physical.
I mean, physically, if you have states left in the left and right, positive energy, negative energy, then this commutes to the constraint. Now we are doing something only on one side.
No, I'm actually doing the cross product on both sides.
Both sides.
Yeah, so it's completely consistent.
Is it going to be important that you're going to compute some entanglement entropy of half with the other half? Or just to define for the whole thing also you need this?
What do you mean to define for the whole thing?
Whole thing, you take the whole spatial slice. It was that type. What was it? That was type 1.
So actually the whole slice is if type 1. So each thing is type 1.
So you are doing this in order to be able to compute it.
Yeah.
I see. So then maybe that's why you can't do my thing, because one is here, one.
So then actually maybe my understanding is not right, because even if I kept the whole slice and I allowed these operators, they would not commute with the Hamiltonian momentum constraints, because they're not.
You have to dress them to make.
No, but you are saying without dressing. I mean, without dressing, now I keep the A. But ALs and A rights as local operators, of course, will not commute with the constraints, right? I'll have to somehow construct operators which commute. So this is a way to get me such operators.
But your only constraint was that the ADM energy doesn't change. That I could have ensured by doing something here and something.
That you could ensure. The other ones you have to work harder.
But the other ones then in perturbation theory you can probably do.
But then there are no non-trivial operators on one side.
Yeah, I suppose that's the point. That's why there's no problem in doing it the whole thing. It's when you cut it that there's an issue. That if you want to cut it and then talk about operators, then you need to dress them.
So at the end of the day, you'll be doing 50 operations on one side and you pick one of the two left or right.
No, you will do this to both, but actually the thing is one of them is trivial because you know that TR and TL are not independent. Only one of them can be made 0, the other one is 1. Okay, so let me just see if I can.
But something's point is, I think it's very one. I mean, maybe probably all of you, but that you're saying that the only way to make a local operator without involving the other side is to dress it to its form. And therefore you need some degree of freedom to dress it. And this was this degree.
At least it makes it sort of more physical, like what they otherwise it seems.
Okay, so now that we have made it type 2, then you can define a trace on the algebra. And let me just stop by showing you what is the trace, and then we can continue tomorrow. So here is the operator in the extended algebra. I just Fourier expanded it in this new h hat plus x, which is actually HL is x. Okay, so just h hat plus h. And where this A naught S is in the original algebra, and I'll just show you what the trace is like. This is what the trace is. Okay. So this A naught S has to have a non-trivial behavior with S in order for this integral to be finite. And this is what the trace looks like. And this trace is unique up to this.
Just don't go too fast. Sorry.
Yeah.
So now because it's type 2, you have this little trace.
Yeah.
And now you're defining it. And now the extended right algebra can be written like that.
Yeah.
Is that X there?
X is the same as HL, sorry. X is the same. It's a new left Hamiltonian that you have added to the system. And this, you can show that this satisfies all the properties of the trace. And psi is the Hartley state.
So compared to the new, the naive thing you would do, like if I was just naively doing it, I would have taken H hat, right? Because H hat is made out of the gravitons energy in the left or right. Here we are doing the right, I guess.
No, H hat is both.
Yeah, H hat is both. But I'm saying
H hat plus X, H hat plus X is HR. Yeah, I'm just writing everything in terms of the left Hamiltonian, but it's actually HR.
I just want to know, make sure I understand. So, what is making the trace better behave? Somehow H hat is doing, X is doing, but X is just it suddenly became much nicer. The divergences and all went away.
No, you have, the divergence goes away. The divergence goes away in the sense you'll be able to define density operators. But here you have to have this A naught of S having some non-trivial behavior in order to make this integral.
But
So it's an algebra where the trace is not defined for all operators, which is a type 2 infinity. Trace of the identity, for example, would be.
To begin with, this is very different from what I would have naively tried to do, right? If you ask me to compute the trace of an operator, I'd choose some basis and I would sum over basis elements and so on. Here you chose one state. The psi was what state? Hartle-Hawking. And then you generated a trace out of that.
That itself is not a trace because we know that for one-sided operators, the Hartle-Hawking state looks like a Bernoulli state with a minus beta H factor. So that's not a trace, right? So I think she's trying to cancel that e to the minus beta energy factor by putting that e to the beta x term. But that sort of cancels that independence.
I see.
And then you have to also integrate over x because now x is a dynamical trace. Somehow magically
I see.
Intuitively.
Okay. I see. You're saying if you had not done the integral and all, then you would have had. But I would have been happy with e to the minus beta h trace. That's not a trace.
It has a KMS property. It's not just trace of AB equals trace of.
I think something is saying the trace involves some over states. Why is there only one particular state?
That state is a global state, right?
Right.
So note that the expectation values of one-sided operators in the global state look like trace of e to the minus beta h times the.
Yeah, and that H there, Onkar is
very naively like the half-sided
modular, right?
Exactly.
That object.
I'm being a bit naive.
No, I agree. Okay, now I understand your comment. Then you're saying now you but it's a very different sort of beast from what you would have naively tried to do, right? Somehow it meets all the trace.
It all meets all the properties.
And does it mean something physical? I mean, at least I understood the whole idea of dressing somewhat physically. This trace means what physically? I mean, I have some. Let me ask you this. Okay, I have some operator which creates a lump of graviton. Yeah, it was unphysical, so I dress it. Okay, now I have the dressed operator, right? And now you.
The trace is just going to make me define the entropy of the algebra. I'll just have some density operators because of this trace. And then I will take minus trace rollover. So let me just show you this is the standard, this would be a standard quantum mechanical formula. Here, this trace is the new trace. Okay. So from this equation, I can define density operators associated with state. And then I can use them to compute an algebra entropy. And what these people did was, so you can compute an algebra entropy by doing this. And I'll just stop here. That what these people found was this algebra entropy is the generalized entropy modulo constant. So you just take your trace, you define these density operators, and then they found that this is true, that the algebra entropy is the generalized entropy at the bifurcation surface of the black hole modulo constant.
And what is the nature of that proof?
What is the nature of that?
That these two are equal?
That I think I have some slides on that. Yeah, I'm going to talk about
You're going
that.
to talk
Yeah, I'm going to talk about
it. Okay, I think you just once to that trace. So X is roughly left.
Yeah, it's left hand.
Left hand.
And so this operator A hat is in the right?
Yeah, A hat is in the right.
It's in the right,
Yeah.
but you want to anyway keep this X factor.
X is now my new degree of freedom. Because there is not 2 degrees of freedom. There's really only one.
Because it's also the right Hamiltonian.
Yeah,
Is just some.
H hat plus X is the right hand.
So basically what it's done is, it is the sort of right thing to exponentiate in that H hat plus X is the nice operator. H hat itself is just graviton is what? Is the energy in the gravitons.
Yeah.
And this includes ADM.
And as Onkar said, this integral is somehow cancelling the fact that there is an e to the power minus beta image. That if you excite more energy on one side, you remove that suppression factor.
Yeah. Okay, so I thought I'll just stop here today and then we will continue from here next time. Is that fun?
Okay.
Yeah. No, sure.
The C that you showed in the next slide.
Let me just go to the next slide. This one?
Next slide.
Okay.
This C. Is it same for all the states that you?
Yes, yes. It's a state independent constant. Yes.
C is state
Yeah.
independent.
C is state.
Okay. And second thing is, why is it called cross product? What's the reason?
I don't know why it's called cross product. It's just this dressing, I think. It's just this dressing. But I don't know why it's called that.
So it's a factor state independent, not as a factor.
I'm sorry.
I thought the definition of the trace involved the state. So the state independence of C and not to be a factor.
Yeah, it is quite non-trivial actually. You have to see the computation to see that. So I'm going to have some couple of slides on that.
Comment about, in quantum field theory, Shiraz, I think you were trying to define trace by subtracting from the vacuum. One problem is that we will use positivity problem. So the trace also has the property that trace of any positive operator is positive. But when you're subtracting something from the vacuum, you're not guaranteed to have the positive trace.
Because you can reduce somehow.
Yeah, I mean, it is possible that there are some operators for which trace of that you are defining this thing.
So you're saying it's a real problem, not that.
No, but I mean, entropies are finite. You can regulate them. And you might get a negative answer. You know, this is like when you renormalize positive operators, you put two dots in normal order, you can get a negative answer.
Yeah.
For phi squared, double dot.
Because you can reduce the entanglement between here and there. You can do something physical. Yeah. But you're saying the positive, that you can define a positive thing may be useful to something.
Yeah.
Sorry, and this business of I understand now after all the discussion that you wanted to have this dressing. Now you implemented this Hilbert space on which this dressing operator can act just completely in an ad hoc manner.
No, the constraint, I implemented the constraint of the Hilbert space, right? That removes one of the factors. No, there's a left Hamiltonian and a right Hamiltonian and a left Hilbert space. And
that's good. That's semiclassical graph. That I got.
Yeah.
I'm saying that you implemented the Hilbert space on which HL acts. You just made it up, right? You said L2 functions. I could have done something else. Probably it doesn't matter.
No, I think it will matter.
Then why
because this whole construction of this trace depends on that, right?
But then why was that the right thing to do? Where did that come from? Where did these L2 functions come from?
As opposed to what?
I don't know. I can make a 10-dimensional Hilbert space and have each acting on some complicated.
Then I think the explanations will also be discrete.
So it is sort of ad hoc.
Many Hilbert spaces with continuous operators.
No, I think it is a bit ad hoc to just add HL and HR like this. But if you add it, this is the smallest thing you could do, right?
Yeah, but I was wondering whether if I did something less, if I did another ad hoc thing, I would
like
get the same
what?
answer.
Like adding.
Gauss law is only for one. Right, so you just do for that. The rest you can just.
It doesn't matter.
The other things can be added.
Is the,
As long as it's got a continuous spectrum, that's all that matters.
But I mean, isn't it true that if you get some different cross product construction, you'd also get different answers for it?
So if you did the cross product by different modular operators corresponding to different states, the algebra you get is the same, apart from an isomorphism.
Take the same state. But I mean, if there is some other possible cross product construction.
That will not give you this, right? So that so you want the constraint to be commuting with operator.
Suppose I take a L2 times L.
Okay.
And I make the Hamiltonian the sum of the two. For instance.
No, but are you doing cross product with which operator are you doing the cross product?
I'm doing whatever you're doing, but I'm just changing the construction of the new ad hoc Hilbert spaces that you construct. So suppose instead of having a particle moving in one dimension, I have a particle moving in two dimensions as my new Hilbert space.
Okay, and then I look at the, I don't know, something, I can make some operator there. Will it change anything or? I'm trying to see if there is physics associated with them, it actually being L2 or it was just some arbitrary.
So you're implementing the cross product with just one operator, right? You have to choose an operator which is the operator HL will act on some Hilbert space which you have added.
Yes.
Is that Hilbert space a tensor product of two or?
Yeah. Instead of L2, I have L2 times L.
The question is, what integrals do you want? Two variables or one variable?
That would be
This conjugation and this integral that we give.
It's like you're adding 2 degrees of freedom. Right?
I'm adding 2 degrees of freedom. So I've got H acting on my Hilbert space, and then I've got the Hilbert space. Then you have to tell me what
No, the Hilbert space seems to correspond to 2 degrees of freedom.
No, let's take just H1. Yeah. H1 now is some operator on some other Hilbert space. It's an operator in the Hilbert space of particle moving in 2 dimensions. Okay. Now you wanted some position operator in that Hilbert space.
I'm thinking of H1 as momentum operator in the Hilbert spaces that we're going to use.
Okay.
Yeah. You have 2 dimensions, there will be 2 momenta.
Okay.
So now what are you doing?
Which one are you going to do the cross product for?
Yeah, I choose some random direction.
No, the other thing will
One, right?
only one, right?
Only one.
Then it will not change it. Then it will not.
But so
it will not change the type of
the
algebra.
structure of your Hilbert space doesn't really matter.
No, it doesn't really matter.
It's a matter of representation, right? E to the ISP is always like just a U1 action, so you can always write it so that it looks like that on a one-dimensional space. The rest of
the rest is
That matters because HR and TR have this non-trivial how you represent it in Hilbert spaces.
I think the best would be like if you, in terms of radius CFT, you have this right, and then there will be an extra quantum mechanics on the right. Roughly, I don't know, that's what it is.
And in the field theory, do we have, is this P degree of freedom the thing that H acts on? Is there some sense that it's there in the field theory? Sorry, propagation.
It's not in the field theory, right? It's extra degree of freedom you're on.
But it's on the boundary.
It's on the boundary.
So it feels like the field theory.
One-sided prostate, one-sided wheel up, no?
So it's, you think it's actually the Hamiltonian of the field.
Yeah.
But the Hamiltonian of the field theory also includes the area.
One-sided.
You mean one-sided answer?
No, but now you've got 3 objects. You've got the left Hamiltonian, you've got the right Hamiltonian, and you've got the area. So it's not really doing the full field theory. Or is it? Because if so, then there's no area Hamiltonian. It's just if you've got really field theory, well.
Each left and each right here are like the semi-classical versions of the boundary number.
Yeah, are there.
Like, in small excitations around the black hole, they can fluctuate. They're like these effective energy, left Hamiltonian, right? So is that what you were saying? And of course, there's a Gauss law constraints which constrain gravity, which relates to the power.
Sure. But I was wondering whether there was this P degree of freedom that you have over X degree of freedom, whatever, whether there was a degree of freedom like that in the field.
It's just, it's in the corresponding operator. Like so the operator is the boundary.
Operator is the boundary Hamiltonian, but there's no L2 on which it acts.
Not really, that's right.
That's somehow some proxy for what it actually does.
I mean, it will change, right? If you act on your state, boundary CFT state, you act with it on that state with HR, I mean, the real CFT on.
It changes to some other state.
Other state, right? That evolution.
So you start with one state and just follow the evolution.
Yeah.
Exactly.
What's
Suneeta gave a talk on this, where he was trying to make this more complete. Where he, here they constructed some base state.
Some observer state.
Some state, and then there's some energies and then what? He acted by this boundary Hamiltonian, and then he showed that time. So he wanted this time band algebra, right? If you remember. So instead of he said that in general, if you allow for all the things that it doesn't exist, but you only consider a set of operators where only finitely many applications of H were allowed, and then if you act with the IHT, then move it to some other place, then that's like a tensor, that's like a direct sum. And then that happens at every value of t. And that's how you get this direct product. Say extra t. But I don't immediately see that kind of relation between this and this also. In what sense the base algebra that Surat had, on which this e to the IHT was acted to get this enlarged algebra, is this type 3 quantum field theory algebra.
Like the bulk operator, right? I mean, you
Bulk
start
operators.
with some heavy state, and then you bulk
Right,
operator.
so that's matches with matches.
Yeah.
So this new degree of freedom has to be something that's not in the, not in the traces. So somehow it's acting just in the gluons, not on the gluons, right? How is that separation? Somehow it's acting but not changing the traces.
Yeah, it's what Abhijit said, right? Like if you keep acting with the Hamiltonian CFT Hamiltonian, then if you do e to the ITH, then at least if the states are, the initial state was heavy, then the new states that you get will be approximately orthogonal. At every value of delta t and so on and so forth, you keep generating orthogonal subspace. Orthogonal little subspace.
I see. So you're saying this is just a label? Around each of these you've got trace states.
Exactly.
But that argument I see for the full microscopic Hamiltonian, right? But in this case, this construction was done with the bulk Hamiltonian. And that it looks like a kind of an operator that is accessible.
This construction can actually be done with the boundary also. So I have been focusing on the bulk because I want to prove things for asymptotically black.
No, but sorry, go ahead.
No, it's the same degree of freedom, right?
Yes. Boundary time. From
the boundary point of view, you see it by boundary Hamiltonian. Here
No, but this acting on gluons and gluons are concerned. This operator, because it's a bulk operator, seems to act on gluons, right? While you want an operator that's acting on gluons in the smaller case. Right? Yeah.
I think HN is not a bulk. It's just wherever you get from the boundary.
No, but as you were saying, this is applying in flat space also.
What?
I mean, this discussion applies to flat space also.
But you need to put some additional operators that were not bulk. Everything, like the integral over the area of Hamiltonian was bulk. So these two are just some abstract additions. I think that is somehow important.
But you can think of those as fluctuations of the boundary area.
Boundary, right? Boundary.
Idiom. Because it had this difference of two boundary terms.
Right. But the Hilbert space, as you guys said, is the Hilbert space of what you get by acting on the gluon. When you do this. So as you say,
from the gravity point of view, you still see, like, because you have access to the ADM. And the energy of the state has changed a little bit. You know that. ADM.
I see.
It's a bit funny because it's like asymptotic properties of the metric calculus.
It's like you're saying you put one additional glue ball on top of this. The only way you can do that is by also increasing the area.
Yeah.
So that you see semiclassical.
Yeah, you see.
Right.
Okay, then microscopically you can add gluons, but as far as now the restriction of that operation on the semiclassical states is concerned, that also you did not have. And then you have that.
And in the field, but in the field theory, you have like some singlet state, which is this very excited state. Now you try to act. I'm trying to understand what this Gauss law is from field theory. Is this somehow related to the UN Gauss law? Or not?
Oh, from the field
theory point of view. in the sense that doesn't sound right, because you could add just you take a singlet, you add the singlet operator, and that's just a singlet.
That also means like taking energy from you.
Right.
Yeah. Equation.
Right. From the boundary point of view, if I was just trying to define entanglement entropy between these two sides of the thermofield at large and in large and negative theory, what is the problem I have there, and how does this solve it?
Well, at finite and there's no problem. Oh, sorry. Right? At finite, there's
Finite and there.
But say I want to take the large end.
Even at large limit in the field theory, what should be?
No, in the large n limit, there's an emergent type 3 algebra.
But it must be that you have to add more than these trace objects. That to get this algebra, that you have to add this H and HR. Can you explain from that point of view why there was a problem to start with?
From when you look at it from gravity.
No, just field.
The field theory, what is the problem? There is no problem.
In taking the large end limit? I feel there should be, but otherwise, why was the problem?
That's because the UV divergence, right?
In gravity, but it should have an analog in the field, a large end limit of the field.
That is n-square.
So if I was just doing field theory, I was looking at thermofield double, and I wanted to define an algebra around the thermofield double state of one side. I should have trouble taking the large end limit.
You have only some operators survive.
But
only some operators survive the large n limit.
So single traces. Suppose I just take
single trace.
And that should somehow be type 3.
It gives you type.
And then you do something and it becomes type 2. What is that story?
So that is actually the original paper of Witten was entirely in the boundary theory. Because there is an emergent type 3 algebra in the boundary theory was shown, and then he worked with a type 3 algebra, and he said that you can do everything in the boundary by taking the CFT Hamiltonian on the right and the CFT Hamiltonian on the left, and you can produce a type 2 algebra.
And will it, perhaps in the next lecture, will it be possible for you just 2 minutes to review that story?
Okay, I can talk about it. Although I'm not worked on it, but I can tell you.
Oh, I can look it up.
Yeah, no, it's a Leuthhäuser and Lewis papers. From Lewis papers.
From Lewis papers, yes.
I mean, the story is just that below the half-page dimension, the bulk is thermal area, so the bulk in the type 1. Above the half-page dimension, the thermal cycle becomes contracted. So now the natural subregion in the bulk that you associate with one side is like a subregion of you for the Cauchy space.
In the bulk, yes.
Yeah, in the bulk. So that,
but you should be able to say this purely from the bulk, right? As something about trace factorization or some which operators you keep. You want to keep operators that have finite correlation functions as n goes to infinity. And in doing that, there should be some problem in defining a trace, which is ameliorated if you add one more operator.
So actually, Lewis papers, he didn't talk about the trace, but he showed that you have an emergent type 3 algebra. He didn't really get into the details of why I should have a trace or something like
that. But then there should be that the type 3 becomes type 2 should also become clear just by looking at large and scaling of covariance.
He was saying, I mean, if I remember correctly, he was saying that a strict Hamiltonian is not a part of the algebra. Because
you get a generalized
one-sided because both the specification value and its fluctuation derivatives. So even if you remove the center of the energy term, I mean, if you subtract it from the specification value of the Hamiltonian, it's still there as in fluctuation derivatives. So at strict large limit, this Hamiltonian is not a part of the algebra. But taking this cross product construction is like including one-by-one correction. So when you take one-by-one correction, particularly you are including this Hamiltonian as a part of this algebra, and that's how you get this.
So say that again. He has to do this. He has to do an.
So divide the Hamiltonian by n.
So everything was clear, right? When you have entanglement on both sides, of this side with that side, you just have this area which is finite. So in field theory, when you compute this entanglement entropy, I thought all this construction has already been done. Only when you want to think of this as coming from the bulk, you have to do this.
But the entanglement entropy of the two sides is infinite, right? Because it's e to the power n squared times entropy.
E to the sorry, what?
In the n goes to infinity level, the entanglement entropy between the two sides is infinite. So if you just define the field theory equation, you get infinity. And as n goes to infinity.
The 1 by Gn in the bulk is basically n square and the boundary, right? You're getting infinite entanglement entropy in the bulk because there is 1 by Gn. The area term. And that corresponds to take length and n square goes to infinity.
And just in the thermophile double, we know that there's infinite entanglement between the two sides, right? E to the power n squared. So there's some trouble that will emerge there. I can completely understand what you said, but
yeah, I mean, he says, I mean, even I don't understand that. But
Hamiltonian is not part of the algebra. Then will be zero. Infinity.
it would be great if you could review this because it feels like you're saying that the field theory makes it. You'll be able to see this just very directly from field theory.
Yeah.
Yeah.
Fact three
It's inevitable that you do.
so this argument you can see.
Wait, sorry. So you are saying
It's
now
a type
this
3.
problem
It's a type 3 algebra that.
I mean,
And then it becomes type 2 once you do something.
Yeah. Once you do the same construction, everything just for the field theory, HR and HM.
I mean, he differs. So what he does is he says that this Hamiltonian is divergent, but h by n square is finite. I mean, h by n square is a well-defined operator, but in the n by infinity limit, this h by n square commutes with all the operators in at a boundary because Hamiltonian commutated with any operators time derivative. But you're dividing this by n square, and you're taking n by infinite limit, which means that h by n square commutes with all the operators. But if you take 1 by n direction, this h by n square now acts non-trivially on the boundary. So you're thinking of this h by n square as one extra in the boundary.
And now you have to do cross product.
Yeah, I mean, for that, he says you have to do some cross product.
Yeah.
So
Now you
then
have
I'm
to.
totally confused. I thought cross product is not solving this issue, but rather the issue of UV divergences of the gravity, where if you want, so if you
But UV divergences n square n goes to infinity.
no, I mean from the bulk, if you think of this quantum field theory in the bulk, you are computing the entanglement of using this. I see that's one over an issue.
That's an issue.
I see.